There's a quiet that exists far beyond the edge of our atmosphere, a profound silence that's deeper than anything we can experience on Earth. But within that silence, the universe is anything but still. It is a cosmic stage for events so strange, so utterly bewildering, that they challenge the very foundations of what we think we know. Out there, right now, stars are dying in ways we can't yet explain. Galaxies are spinning in impossible configurations, and signals are echoing across the void that hint at phenomena with no name in our science books. We look up at the night sky and see a tapestry of familiar lights, but what we're seeing is only the tiniest fraction of the truth, a calm surface hiding an ocean of cosmic mysteries waiting to be discovered. Today, we are setting off on a journey into that profound unknown to explore 30 of the most bizarre and newly discovered space oddities. These aren't just curiosities, they are cosmic anomalies that have left astronomers and physicists both thrilled and perplexed. We will encounter stars that burn with fuels that shouldn't exist, black holes that behave in ways that defy the laws of physics, and entire galaxies that appear to be missing the very glue that holds them together. Each discovery is a piece of a puzzle we are only beginning to assemble, a whisper from the cosmos that reminds us how much we have yet to learn. This is not a tour of the familiar planets and constellations. This is a voyage to the frontier of human knowledge, to the very edges of our understanding. So prepare to have your perception of reality stretched and reshaped. As we dive into these cosmic wonders, remember that each oddity is more than just a scientific headline. It is a testament to the enduring human spirit of curiosity. It represents a question asked into the darkness and an answer that, for now, only leads to more profound and exciting questions. This journey is about embracing the wonder of not knowing and finding inspiration in the sheer scale of the mysteries that remain. Let's begin our exploration of the 30 strangest, most mind-bending discoveries that are currently rewriting our map of the universe. Our journey into the cosmic unknown begins not with a flash of light, but with a profound and puzzling chill. Picture the very first light of the universe, a fading afterglow from the Big Bang that still permeates all of space. This cosmic microwave background is like a fossilized imprint of creation itself, and for the most part, it's remarkably uniform. But nestled within this sea of microwave static lies our first oddity, a cosmic anomaly of staggering proportions known simply as the Great Cold Spot. Discovered by the incredibly sensitive Planck satellite, this region is not just a little cooler than its surroundings. It is a colossal void of cold, stretching over 1 billion light-years across. To put that almost incomprehensible scale into perspective, if our entire Milky Way galaxy were a grain of sand, this cold spot would be larger than the entire continent of North America. Its existence is a direct and uncomfortable challenge to one of cosmology's most cherished principles, the idea that on the largest scales, the universe should be roughly the same everywhere. Scientists have wrestled with this discovery since it was confirmed. The most straightforward explanation would be that it's a vast supervoid, an enormous region of space with far fewer galaxies, and thus less matter to warm the background radiation. Yet, when astronomers mapped the area, they found it isn't empty enough to account for the extreme temperature drop. The cold spot is simply too cold for the void we see. This discrepancy has forced physicists to consider far more exotic possibilities. One of the most mind-bending theories suggests that this cold spot is a cosmic bruise, a remnant of a colossal collision between our universe and a bubble of another universe in the vast multiverse. In this scenario, the energy drained away during this unimaginable impact left behind a permanent cold signature on the fabric of our reality. While this idea remains highly controversial, its mere consideration highlights just how revolutionary this discovery truly is. It forces us to ask if the anomalies we detect are not just quirks of our universe, but evidence of something entirely beyond it. From the vast chill of a cosmic anomaly, we now turn our attention to a discovery of breathtaking and almost artificial beauty. If the Great Cold Spot is a puzzle written in the language of temperature, our second oddity is a riddle carved from light and gravity. Astronomers have long been captivated by Hoag's object, a nearly perfect ring galaxy that for decades stood as a unique cosmic jewel, a brilliant circle of young, blue stars orbiting a much older, golden core with a seemingly empty gap of darkness between them. It appeared to be a one-of-a-kind wonder, a celestial donut that defied the typical messy, spiral-armed structure of most galaxies. But recent observations have revealed that it is not alone. We have now found a second ring galaxy, so pristine and symmetrical that it has been dubbed Hoag's Object 2.0, and its existence is challenging our understanding of how galaxies live and die. This newfound galaxy is a spectacle of cosmic architecture. Through the lens of powerful telescopes, it presents an almost impossibly perfect circle. Its ring is a vibrant band of intense star formation, glowing with the blue light of countless newborn suns. This ring is perfectly balanced around a central core of older, redder stars, and separating the two is a profound void, a gap so clean and dark it looks as though it was drawn with a cosmic compass. The sheer symmetry is what stops astronomers in their tracks. In our universe, which often favors chaos and irregularity, such perfection is incredibly rare and demands an explanation. The central mystery is the same one that has puzzled scientists about the original Hoag's object. How did this structure form without a visible central bar? In most ring galaxies we observe, the elegant circle is a temporary illusion created by a central bar of stars. Think of this bar as a kind of gravitational delivery system. As it rotates, it funnels gas and dust outward along its length, eventually sparking star formation at the ends, creating a ring. But in both the original Hoag's object and this new, even more perfect version, there is no sign of such a bar. The central core is smooth and round, offering no obvious mechanism to create the stunning ring that encircles it. This leaves astronomers with a handful of compelling yet imperfect theories. The leading hypothesis is a galactic collision, a rare bull's-eye impact where a smaller galaxy passed directly through the center of a larger disk galaxy billions of years ago. This event would have sent ripples of density waves through the disk, much like a pebble dropped in a pond, compressing gas and triggering star formation in a perfect expanding circle. Over eons, the intruder galaxy would have moved on, leaving behind this nearly flawless ring as the only evidence of the violent encounter. Yet, even this dramatic explanation has its problems. The ring of Hoag's Object 2.0 is so perfectly circular and undisturbed that it suggests a collision of unimaginable precision. There's no sign of the residual distortion or tidal tails that such a massive gravitational interaction should leave behind. The alternative theory is that it formed this way in isolation, a product of extremely rare and stable conditions in the early universe. But this idea is equally challenging, as our current models of galaxy evolution don't easily account for such a serene and symmetrical birth. The discovery of this second perfect ring galaxy transforms the original from a cosmic oddity into a potential category. It suggests that the processes we thought were rare might be more common, or that there are fundamental mechanisms of galactic evolution that we have not yet begun to understand. This isn't just another pretty picture from space. It is a profound question about the very forces that shape the universe's largest structures. This discovery brings us from the grand architecture of entire galaxies to an intimate puzzle right here in our own cosmic neighborhood. Tucked away in the halo of the Milky Way, a relatively faint star designated HD 140283 holds a secret that strikes at the very heart of cosmology. By all accounts, this star appears to be a senior citizen of the universe, but when scientists calculated its age, they were met with a result so baffling it seems to defy logic. The best estimates suggest this star is approximately 14.5 billion years old. Now, that number might not immediately ring alarm bells until you place it next to the current best estimate for the age of the universe itself, which is about 13.8 billion years. According to these measurements, this star would be older than the cosmos it resides in, a clear impossibility that points to a fundamental flaw in our understanding, either of the star, the universe, or both. This is the paradox of the Methuselah star, and it has ignited a fierce and fascinating debate among astronomers. To understand why this age is so controversial, we need to look at how scientists determine the age of such ancient stars. They don't have a birth certificate to consult. Instead, they perform a kind of cosmic detective work based on the star's chemistry. Stars like HD 140283 are population 2 stars, meaning they are among the second generation of stars to form after the Big Bang. They contain very low amounts of metals, which in astronomy means any element heavier than hydrogen and helium. This metal-poor composition is a key clue to their great age, because in the very early universe, only the primal elements of hydrogen and helium existed. The first generation of stars, called Population 3, forged the heavier elements in their nuclear furnaces and then scattered them across space in violent supernova explosions. The fact that the Methuselah star has some metals but very few places it firmly in that second wave of stellar formation. By meticulously measuring the precise amounts of certain elements, particularly uranium and thorium, and applying our knowledge of stellar evolution and nuclear decay, astronomers can arrive at an age estimate. The problem is that this estimate, when done with the greatest care and with the most advanced instruments, still gives us a number that seems to break the rules of reality. So, how do we resolve this paradox? The scientific community has approached the problem from several angles, each with profound implications. The first possibility is that our measurement of the star's age, while sophisticated, contains a hidden error. The calculations depend on extremely precise measurements of the star's composition, its brightness, its distance, and its position on the Hertzsprung-Russell diagram, which charts a star's life cycle. A small miscalibration in any of these factors could throw the final age estimate off by a significant margin. Some recent studies, incorporating data from the Gaia spacecraft that provides exquisitely accurate distance measurements, have suggested a revised age for the star that is closer to 12 billion years, which would neatly place it within the lifetime of the universe. This is the most conservative solution, suggesting that the paradox is simply a result of imperfect data. A second, more intriguing possibility is that our understanding of stellar physics itself is incomplete. The models we use to describe how stars burn their fuel and evolve over billions of years are based on our best theories, but they are just that, models. They are built on assumptions about processes happening deep within a star's core, places we can never directly observe. Perhaps there are unknown physical processes at work in these ancient metal-poor stars that alter their rate of aging in ways we haven't yet accounted for. If this is the case, then the Methuselah star isn't an error. It's a teacher pointing us toward a more nuanced and accurate theory of how stars truly live and die. The most radical explanation, and the one that truly captures the imagination, challenges not the star's age, but the age of the universe. What if our measurement of the cosmos's birthday is wrong? The 13.8 billion year figure is derived from the lambda-cold dark matter model, the reigning standard model of cosmology, which is itself built upon measurements of the cosmic microwave background and the accelerating expansion of the universe. If the Methuselah star is genuinely older than that, it could be a direct piece of evidence that our cosmological model is missing a crucial piece. This wouldn't mean the Big Bang didn't happen, but it might mean that the early universe evolved differently than we think, perhaps requiring new physics involving dark matter or dark energy. While this is considered a long shot by most cosmologists, The mere fact that a single star can force us to entertain such a profound question demonstrates its incredible importance. It serves as a powerful reminder that sometimes the smallest clues can point to the biggest truths, and that our map of the cosmos is still very much a work in progress. Just when we think we understand the rules of cosmic architecture, the universe presents us with a paradox of emptiness. If the Methuselah star challenged our sense of time, our next oddity confronts us with a staggering void in space itself. Known as the Oddities void, this region is one of the largest known structures in the universe, a spherical chasm of near-nothingness so vast it could contain thousands of galaxies like our own, yet for decades only a handful have been found there. It is a cosmic desert on a scale that is almost impossible to fathom, a gaping hole in the large-scale structure of the cosmos that resembles a bubble in Swiss cheese. Only this bubble is over 300 million light-years across. For a long time, astronomers considered this void to be a monument to emptiness, a place where the usual rules of galaxy formation had seemingly failed. But a recent discovery has turned this idea on its head, revealing a solitary galaxy cluster sitting right in the void's heart, a finding as perplexing as finding a bustling metropolis in the middle of the Sahara. The existence of the Oddities void has always been a puzzle. According to our prevailing models of the universe, matter should be distributed in a vast cosmic web, with filaments of dark matter acting as a scaffolding upon which galaxies and clusters form. The voids between these filaments are expected to be empty, but the sheer scale of the Oddities void pushes the limits of that theory. It is so profoundly empty that its discovery in the 1980s was met with a mix of awe and skepticism. How could the processes that shaped the universe leave behind a region this barren? The leading hypothesis was that it formed through the merger of smaller voids over billions of years, a gravitational clearing out that left behind an immense pocket of near vacuum. Finding galaxies within it was like searching for a few specific grains of sand in an enormous, empty warehouse. You wouldn't expect to find anything, let alone a significant grouping. This is why the recent detection of a galaxy cluster at the very center of the void is so revolutionary. Using some of the world's most powerful telescopes, astronomers have pinpointed a small collection of galaxies bound together by gravity, shining like a lone campfire in an otherwise lightless expanse. This isn't just one lonely galaxy. It's a cluster, which implies that the conditions necessary for multiple galaxies to form and congregate existed in a place we thought was fundamentally hostile to such activity. The presence of this cluster forces a dramatic re-evaluation of our understanding of voids. It suggests that they are not completely empty after all, but may contain faint, underlying structures, whispers of the cosmic web, that we have not been sensitive enough to detect until now. This resident cluster is a relic, a surviving testament to a pocket of matter that somehow resisted being swept away by the forces that cleared out the rest of the void. The implications of this discovery ripple outward, touching on two of the greatest mysteries in cosmology: dark matter and the formation of large-scale structure. Galaxies and clusters don't just form anywhere, they coalesce where dark matter has pooled most densely, creating the gravitational wells that attract normal matter. The existence of this cluster in the void's center strongly suggests that there must be a significant, previously undetected clump of dark matter anchoring it in place. This invisible halo acted as a seed, gathering enough gas and dust to birth these galaxies against all odds. Its presence challenges models of how dark matter is distributed, indicating that even the emptiest regions of the universe might be threaded with faint tendrils of this mysterious substance. We may need to adjust our simulations to account for a more complex, fine-grained distribution of dark matter, one that allows for such unlikely oases to exist. Furthermore, this finding forces us to reconsider the very nature of cosmic voids. Rather than being completely barren wastelands, they might be better thought of as the universe's quiet backwaters, regions with extremely low density but not zero structure. The galaxy cluster in the Boötes void could be the tip of the iceberg, hinting at a population of faint, dwarf galaxies or isolated stars that have so far eluded our detection. This transforms our view of the cosmic web from a simple picture of bright filaments and dark voids into a far more intricate tapestry, with varying shades of density everywhere. The void is not empty, it is simply a different kind of neighborhood with its own unique history. This lonely cluster is more than just an astronomical curiosity. It is a crucial data point, a key that is helping to unlock a deeper understanding of how the universe built its largest structures from the subtle gravitational influence of the unseen. Leaving the vast emptiness of the Boötes void behind, we now encounter a cosmic object of almost unimaginable value and strangeness. Our journey brings us to a planet that defies every expectation of what a world can be, a place where the very ground beneath your feet would be a glittering expanse of crystallized carbon. You may have heard of the famous diamond planet PSRJ 17191438b, a world that captured the public's imagination as a celestial jewel. But recent discoveries have revealed that this exotic world is not a solitary freak of nature. Astronomers have now confirmed the existence of its twin, a second planet that is also composed largely of diamond, orbiting a rapidly spinning stellar corpse known as a pulsar. The discovery of a second such world transforms a fascinating oddity into a potential new category of planets, suggesting that the universe might be crafting these precious worlds more often than we ever dreamed possible. To understand how such a bizarre planet can exist, we first need to look at the violent and dramatic life of its host star. A pulsar is the ultra-dense, city-sized remnant of a massive star that went supernova. This core, called a neutron star, spins at a phenomenal rate, often hundreds of times per second, emitting beams of intense radiation from its magnetic poles. Like a cosmic lighthouse, these beams sweep across space, and if one of those beams points toward Earth, we detect it as a regular, repeating pulse of radio waves, hence the name pulsar. The planet in question, currently known by its less poetic catalog number, orbits just such an object. It was discovered using the pulsar timing method, where astronomers detect the slight, rhythmic wobble in the pulsar's incredibly regular beat, a telltale sign that the gravity of an orbiting planet is gently tugging on it. The characteristics of this wobble revealed a planet with a density so high that only one material fits the profile: crystallized carbon, or in other words, diamond. The formation story of a diamond planet is a tale of cosmic catastrophe. It begins with a binary star system where two stars are locked in a mutual orbit. One of these stars is a massive star that lives fast and dies young, exploding as a supernova and leaving behind the pulsar. The incredible energy from this explosion strips away the outer layers of the companion star, leaving behind only its incredibly dense core. This core, which was once a star itself, is now a naked ball of mostly carbon and oxygen, a white dwarf. But the story doesn't end there. The pulsar's intense gravity begins to pull material from this white dwarf companion onto itself. Over millions of years, this process, known as accretion, steals so much mass from the white dwarf that it can no longer sustain its own structure. What remains is a planet-sized object, but one with the composition of a stellar core. Under the immense pressure of its own gravity, the carbon within this remnant crystallizes, creating a world that is, for all intents and purposes, a giant diamond. What makes the discovery of this twin so significant is how it challenges the uniqueness of the original diamond planet. PSRJ 17191438b was considered a 1 in a billion find, a testament to a specific and rare sequence of events. Finding a second one demonstrates that the conditions necessary for their creation, a binary system with the right kinds of stars, a supernova that doesn't completely destroy the companion, and a subsequent period of accretion must occur with some regularity throughout the galaxy. This forces astronomers to refine their models of stellar evolution and binary star interactions. It suggests that our galaxy may be sprinkled with these dark, glittering relics of stellar cannibalism, invisible to optical telescopes because they emit almost no light of their own, but detectable through the patient monitoring of pulsar clocks. The existence of these twins opens up a new field of study into the ultimate fate of binary systems and the exotic states of matter that can exist under such extreme pressures. They are not just celestial curiosities, they are extreme laboratories offering us a glimpse into the incredibly dense and strange forms that matter can take when subjected to forces far beyond anything we can create on Earth. But if a diamond planet challenges our ideas of what a world can be, our sixth oddity threatens to overturn one of the most fundamental pillars of modern astronomy. We now turn our attention to a ghostly galaxy known as NGC 1052-DF2, a discovery that has ignited one of the most heated debates in cosmology because it appears to be missing something that should be everywhere: dark matter. For decades, the existence of this mysterious, invisible substance has been the cornerstone of our understanding of the universe. We believe it makes up about 85% of all matter, acting as an invisible gravitational scaffold upon which galaxies are built. Without the immense gravitational pull of a dark matter halo, according to our models, a galaxy simply couldn't form or hold itself together. The stars would fly apart. Yet NGC 1052-DF2, a large, diffuse galaxy, seems to be doing just fine without it. This isn't just a missing puzzle piece, it's a piece that suggests the entire picture we've been looking at might be wrong. The story of this galaxy's discovery is a tale of meticulous measurement and growing disbelief. NGC 1052-DF2 is an ultra-diffuse galaxy, a type of galaxy that is as wide as the Milky Way but contains only about 1% of the stars. It's a faint, wispy collection of stars that you could see right through. When a team of astronomers led by Pieter van Dokkum at Yale University set out to study it, they expected to find the telltale signs of a massive dark matter halo. They measured the velocities of 10 glowing globular clusters, which are dense groups of stars that orbit the galaxy's center. The speed of these clusters is a direct measure of the galaxy's total mass, both the visible stars and the invisible dark matter. The faster they move, the more mass there must be holding them in orbit. To their astonishment, the clusters were moving surprisingly slowly. The calculations showed that the total mass of the galaxy was almost exactly equal to the mass of its visible stars. There was no room left for dark matter. It was as if they had weighed a person and found that their weight was exactly the weight of their clothes with no body inside. The immediate reaction from the scientific community was a mix of fascination and profound skepticism. The finding was so disruptive that many astronomers' first instinct was to look for an error. Could the distance to the galaxy be wrong? If it were closer than assumed, the galaxy would be smaller and less massive, making the dark matter discrepancy disappear. Alternative teams rushed to make their own measurements, leading to a tense back and forth in scientific journals. Some studies initially supported a closer distance, but subsequent, more precise observations, including data from the Hubble Space Telescope, have largely confirmed the original team's distance measurement, strengthening the case that this galaxy is truly an anomaly. Other critics suggested that perhaps our understanding of the globular clusters was flawed, or that the galaxy was recently torn apart by a gravitational interaction, scattering its dark matter. Yet NGC 1052-DF2 shows no signs of such a violent past. It is calm, serene, and intact. If we accept that this galaxy genuinely lacks dark matter, the implications are staggering. It creates a paradox that cuts to the heart of cosmology. On one hand, the existence of dark matter is primarily inferred from its gravitational effects on galaxies. If a galaxy can exist without it, that seems to undermine the very evidence for dark matter's existence. On the other hand, the fact that this galaxy is such a profound outlier actually strengthens the case for dark matter everywhere else. It demonstrates that visible matter and dark matter are not inextricably linked. They can, under rare circumstances, be separated. This suggests that dark matter is a real, physical substance that can be stripped away, rather than just a flaw in our theory of gravity. The discovery forces us to ask a much deeper question. How did this galaxy form? If dark matter is necessary for galaxy formation, how did NGC 1052 DF2 come into being without it? One compelling theory involves a dramatic cosmic collision. The galaxy resides near a massive elliptical galaxy, NGC 1052. The hypothesis is that billions of years ago, as vast clouds of gas were drawn into the gravitational well of the larger galaxy to form new stars, the dark matter and the normal matter were separated. The dark matter, which doesn't interact with itself or other matter except through gravity, would have streamed through this region unaffected. The normal gas, however, would have collided with other gas, creating friction and heat, slowing it down and causing it to coalesce into stars right where it was. In this scenario, the stars of NGC 1052 DF2 formed from a pocket of gas that had been forcibly divorced from its dark matter partner. This would make the galaxy a cosmic orphan, a collection of stars born without the invisible anchor that defines every other galaxy we know. The discovery of a second, similar galaxy in the same region, NGC 1052 DF4, which also appears to be missing dark matter, lends strong support to this formation theory, suggesting it might be a unique outcome of this specific galactic environment. The controversy surrounding NGC 1052 DF2 is far more than an academic debate. It is a perfect example of the scientific process in action. A radical claim is met with intense scrutiny, forcing more precise observations and the refinement of theories. Whether this galaxy ultimately proves to be completely devoid of dark matter or simply has an unexpectedly small amount, it has already achieved something remarkable. It has pushed astronomers to question their most basic assumptions and to explore new, previously unthinkable pathways for galactic evolution. This oddity is a powerful reminder that every time we think we have the universe figured out, it delivers a surprise that sends us back to the drawing board, humbled and excited to learn more. Our next discovery reads like science fiction, featuring a celestial behemoth on the run. Imagine a supermassive black hole, an object with the mass of 20 million suns, not sitting serenely at the center of a galaxy as they always do, but instead hurtling through the dark voids between galaxies at a staggering 4 million miles per hour. This isn't a slow drift, it's a full-blown cosmic escape. And as if this renegade black hole wasn't astonishing enough, it is not traveling alone. Telescopes have captured an image that is as beautiful as it is bizarre. A brilliant, narrow trail of young, blue stars stretching an incredible 200,000 light-years behind it, twice the diameter of our entire Milky Way. This luminous contrail is the black hole's wake, a spontaneous stellar nursery born from the chaos of its flight. The prevailing theory for this incredible event is a gravitational event of almost unimaginable scale, a cosmic slingshot involving 3 supermassive black holes. The story likely began when 2 galaxies collided and merged. At the hearts of these galaxies were 2 supermassive black holes, which eventually spiraled toward each other, forming a binary pair. Then a third galaxy, with its own supermassive black hole, entered the scene. In the complex gravitational dance that followed, one of the black holes was ejected at tremendous speed. This is the principle of a gravitational slingshot. When 3 massive bodies interact, the lightest one can be flung away with immense kinetic energy, while the other 2 recoil in the opposite direction. In this case, the runaway black hole was the one cast out, and as it plunged through the intergalactic medium, it did something extraordinary. The black hole isn't just plowing through empty space, it's racing through a diffuse fog of gas that lingers between galaxies. Normally, this gas is too cold and spread out to collapse and form stars, but the passage of the black hole creates a shock wave, compressing and heating the gas in its path. Furthermore, the black hole is likely surrounded by an intensely bright, swirling disk of accreted material. The radiation from this disk is so powerful that it ionizes the gas, and the combination of this radiation pressure and the gravitational turbulence creates the perfect conditions for star birth. The black hole essentially plows a cosmic furrow, tilling the inert gas and sowing it with seeds of light. The stars left in its wake are not random. They are a chronological record of its journey, with the youngest stars glowing brightly right behind it. This discovery profoundly impacts our understanding of black hole dynamics and galaxy evolution. Firstly, it provides the strongest observational evidence yet that supermassive black holes can indeed be ejected from their host galaxies, a prediction of theoretical models that had never been confirmed so dramatically. This suggests that there could be many such rogue black holes wandering the dark seas of intergalactic space, invisible to us because they have left their bright accretion disks behind. Secondly, it reveals a new and unexpected method of star formation, one not tied to the gentle rotations of a spiral galaxy or the violent collisions of merging galaxies, but to the sheer kinetic energy of a runaway gravitational monster. This forces us to reconsider what triggers the birth of stars, showing that even the most destructive forces in the universe can be creative. The trail of stars is a testament to this duality, a stunning signature of chaos and creation written across the cosmos. While the runaway black hole shows the dynamic violence of mature galaxies, our next discovery reaches back to the very dawn of cosmic time to present a puzzle of a different kind. A galaxy that seems to have been born impossibly old. We are accustomed to thinking of the early universe as a primitive place, a cosmic dark age where the first structures were just beginning to clump together from the primordial soup. But the galaxy known as G092150++, observed by the James Webb Space Telescope, shatters that image. This galaxy is not a faint, infantile collection of stars. It is a massive, fully formed and tranquil disk galaxy that we see as it was when the universe was a mere 1.5 billion years old. To put that youth into perspective, that's only about 10% of the universe's current age. Finding a galaxy like our own Milky Way at such an early epoch is the cosmic equivalent of finding a fully grown adult in a kindergarten classroom. Its existence defies our most detailed computer simulations of galaxy formation, which simply cannot build something so massive and so orderly in such a short amount of time. The sheer mass of this galaxy is the first point of contention. Based on its brightness and the characteristics of its light, astronomers have estimated that it contains hundreds of billions of stars, a stellar population on par with our own galaxy today. But according to the prevailing lambda cold dark matter model, the universe needed time for gravity to work. After the Big Bang, the cosmos was a nearly smooth expanse of dark matter and gas. Tiny quantum fluctuations provided the seeds for structure, but it took billions of years for these seeds to grow, first into small clumps, which then merged through violent collisions to form larger galaxies. The models predict that the universe's toddler years should be dominated by small, irregular, and clumpy protogalaxies, not the vast, serene spiral we see in G092150++. For this galaxy to have assembled so many stars so quickly, the early universe must have been far more efficient at star formation than we ever thought possible, operating at a pace that borders on the miraculous. Perhaps even more baffling than its mass is its structure. The James Webb Space Telescope's sharp infrared vision didn't just detect a blob of light, it revealed a distinct, well-ordered rotating disk. This is a signature of stability. For a galaxy to form a disk, it must have accumulated its mass through a relatively calm and steady process, like a gentle rain of gas over time, rather than through the chaotic and disruptive series of major mergers that our models suggest were common in the early universe. A giant merger would have stirred up the galactic material, destroying any delicate disk structure and leaving behind a more elliptical, puffy shape. The presence of this mature disk so early on suggests that some galaxies in the infant cosmos somehow bypassed the period of violent collisions altogether, forming with an elegance and speed that we are only beginning to comprehend. It hints at unknown physical processes that allowed gas to cool and collapse into stars with breathtaking efficiency, perhaps facilitated by different conditions in the primordial gas or by a more influential role for dark matter. This discovery creates significant tension with the standard model of cosmology. The model itself is incredibly successful at explaining the universe on the largest scales. Its expansion, the cosmic microwave background, the distribution of galaxies across billions of light years. But G092150++ is a challenge from the small scale, a single data point that shouts that our understanding of the details of galaxy formation is incomplete. One way to resolve the tension is to question our measurements. Perhaps the distance to the galaxy is wrong, placing it closer to us and therefore making it smaller and less massive. However, multiple teams have confirmed its extreme redshift, firmly placing it in the universe's infancy. Another possibility is that our estimates of its mass are inflated. Maybe the galaxy is filled with a much dustier environment than assumed, which would make its stars appear dimmer and lead us to overestimate how many are actually there. While this is an active area of investigation, initial analyses suggest that even accounting for dust, this galaxy remains anomalously massive. If the observations hold, cosmologists are faced with a thrilling dilemma. They must either find a way to tweak the physics within the standard model to allow for hyper-efficient galaxy formation, or they must consider that the model itself needs a fundamental adjustment. Some theorists are exploring the role of supermassive black holes, suggesting that their intense radiation in the early universe could have pumped energy into surrounding gas, actually preventing stars from forming too quickly. This galaxy, however, suggests the opposite was true. Others are looking at the nature of dark matter. The standard model uses cold dark matter, meaning its particles move slowly. But what if dark matter is warm, with particles moving at a significant fraction of the speed of light? This warm dark matter would suppress the formation of small-scale structures, potentially allowing larger galaxies to form more quickly by streamlining the process. The existence of this impossibly ancient galaxy is a direct invitation to explore these more exotic ideas, pushing the boundaries of our cosmic knowledge. It serves as a powerful reminder that every new window we open onto the universe, like the James Webb Space Telescope, doesn't just show us what we expect to see. It reveals wonders that force us to rethink our deepest assumptions about cosmic history. And just as we grapple with the mysteries of the early universe, our own time presents a puzzle of an entirely different shape, literally. In the vast fields of data from radio telescopes, astronomers have stumbled upon something so strange and unprecedented that they didn't even have a name for it, leading to the straightforward, yet wonderfully candid, classification of odd radio circles, or ORCs. These are not faint smudges or tiny points of light. They are colossal, ring-shaped structures, some so large that they could easily engulf entire galaxies, and yet they are completely invisible to optical, infrared, and X-ray telescopes. They reveal themselves only in the specific wavelength of radio waves, appearing as ghostly halos etched onto the cosmic background. Their discovery was a complete accident, a classic case of finding something you weren't even looking for, and they have since become one of the most tantalizing enigmas in modern astronomy. The story of their discovery begins with the revolutionary Australian Square Kilometre Array Pathfinder, or a SKAP, a network of radio dishes designed to map the sky with unprecedented speed and sensitivity. While conducting a survey to catalogue distant galaxies, astronomers noticed a handful of perfect circular rings that didn't correspond to any known object. At first, they were dismissed as potential artifacts, glitches in the data processing, or side lobe interference from the telescopes themselves. But after painstakingly eliminating every possible instrumental error, the circles remained. They were real. What makes them so perplexing is their combination of immense scale and their elusive nature. A typical ORC can span 1 million light years across, meaning light would take that long to travel from one side to the other. If one were bright enough to see with our eyes, it would appear larger than the full moon in our sky, a testament to its unbelievable physical size. Yet, despite their grandeur, we have no idea what they are made of or what phenomenal event could have blown such perfect, enormous bubbles in the fabric of space. The leading theories attempting to explain these odd radio circles are as fascinating as the objects themselves, each one pushing the boundaries of known physics. One of the most prominent ideas is that we are witnessing the aftermath of a cataclysmic event on an unimaginable scale, a shockwave from a titanic explosion. This could be the remnant of a supermassive black hole eruption that occurred millions of years ago. At the centers of many galaxies, black holes go through periods of intense activity, spewing out colossal jets of energy. If such an eruption happened in the distant past, it could have sent a spherical shockwave expanding outwards through the thin intergalactic medium. As this shockwave travels, it would accelerate electrons to near light speed, causing them to emit synchrotron radiation, which we detect as radio waves. This would create a perfect expanding shell, exactly the kind of structure we see. The reason we don't see a central galaxy or an active black hole now is that the eruption is long over. We are observing the fading echo of a cosmic blast from eons past. A second, even more dramatic hypothesis links the ORCS to a different kind of cosmic violence, the collision of two neutron stars. When these ultra-dense stellar corpses spiral together and merge, they are known to produce gravitational waves and short gamma-ray bursts. Some theorists suggest that such a merger could also unleash a powerful, rapidly expanding fireball of charged particles. If this fireball were to plow into the surrounding interstellar medium, it could generate a spherical shockwave that would glow brightly in radio wavelengths for thousands of years. This theory is appealing because it could explain why ORCS appear to be isolated without a central engine, as the merging stars would effectively destroy each other in the process, leaving behind only the expanding remnant. Yet, there are features of the odd radio circles that don't fit neatly into these explosion-based models. Some of them appear to have a brighter, more structured ring, and there are hints of a central galaxy in at least one case, visible only at specific infrared wavelengths. This has led to a third, truly mind-bending possibility, that ORCS are the throats of wormholes. According to some speculative theories in cosmology, a traversable wormhole, a tunnel through space-time, could, under certain conditions, have a mouth that would appear from the outside as a sphere. The intense gravitational fields at the entrance could potentially accelerate particles and generate the kind of radio emission we observe. While this is considered the most speculative of the theories, the fact that it is even being seriously discussed in scientific papers highlights just how mysterious these circles truly are. They force us to consider explanations that were once confined to the realm of theoretical physics and science fiction. The true significance of the ORCS lies not in which theory might eventually prove correct, but in what they represent, a brand new class of astronomical object. For centuries, we have been cataloging the universe, stars, galaxies, nebulae, thinking we had a handle on the major players. The discovery of something as large and obvious as a ORC, something that had been hiding in plain sight simply because we weren't looking in the right way, is a profound humbler. It tells us that our map of the cosmos is still riddled with blank spaces, and that the universe continues to hold surprises on the grandest of scales. These mysterious radio circles are a direct challenge, an invitation to build new telescopes and develop new theories. They remind us that the greatest discoveries are often the ones we never expected to make, the strange signals that whisper of phenomena we have not yet even begun to name. But if the ghostly rings of ORCS represent mysteries on a truly cosmic scale, our 10th oddity brings the enigma much closer to home, to a single, unassuming star that has become one of the most debated objects in the galaxy. Known as Boyajian star, or by its less poetic catalog number KIC 8462852, this star behaves like no other. Most stars, including our own Sun, have a steady, reliable brightness with only minor, predictable dips caused by sunspots or the occasional passing planet. Boyajian's star, however, flickers. It experiences dramatic, irregular, and utterly bizarre dips in its light, with its brightness sometimes plummeting by as much as 22%, a staggering amount that would require an object far larger than a planet to pass in front of it. The pattern of these dimming events is chaotic, with no discernible rhythm or periodicity, suggesting that whatever is causing the blockage is not a simple, orderly system, but something profoundly strange and complex. The mystery of this star was first uncovered by citizen scientists as part of the Planet Hunters project, which enlisted the public to help sift through the immense volume of data from NASA's Kepler Space Telescope. Kepler's primary mission was to detect the subtle, repeating dips in starlight caused by planets transiting or passing in front of their host stars. The volunteers flagged this one star as being unlike any other, and when professional astronomer Tabitha Boyajian led the investigation, she found a light curve that defied all conventional explanation. There were deep, sharp dips that lasted for days and broader, shallower dimmings that stretched on for weeks. The signature was not that of a clean, spherical planet crossing the star's face, but of something with an irregular, clumpy structure, something that was blocking the light in a way that seemed almost purposeful in its strangeness. The immediate challenge was to find a natural explanation that could account for such extreme and irregular behavior. The first and most conservative hypothesis pointed to a vast, swirling swarm of comets. The idea was that a family of icy bodies, perhaps disturbed by the gravity of a passing star, had been pulled into a highly elliptical orbit around Boyajian's star. As this colossal cloud of comets passed in front of the star from our perspective, the irregular shapes and varying densities of the individual comets and their debris tails could create the jagged, unpredictable dimming patterns we observe. This explanation had the advantage of relying on known physics, but it also pushed the known to its absolute limit. To cause dips as deep as 22%, the swarm would need to be unimaginably vast, containing millions or even billions of comets, a number that dwarfs anything in our own solar system's Oort cloud. While not impossible, it strains credibility to think that such an event would be common, making the star a truly rare anomaly. As the comet swarm theory struggled to answer all the questions, a more speculative and captivating idea emerged, one that captured the public imagination like few other astronomical discoveries: the possibility of alien megastructures. Astronomer Jason Wright and others suggested that the light pattern could be consistent with a vast, incomplete array of solar collectors, known as a Dyson swarm, built by an advanced civilization to harness the energy of their star. Such a structure would not be a solid shell, but a dense collection of orbiting panels, which would block the star's light in an irregular, asymmetrical way, much like the data showed. The hypothesis was never presented as the most likely scenario, but rather as a last resort idea that needed to be considered once natural explanations were exhausted. It served a vital scientific purpose, forcing astronomers to think creatively and to explicitly state what kind of signature an advanced technological civilization might leave on its star. Since the initial discovery, the plot has only thickened. Follow-up observations have revealed even more baffling behavior. Not only does the star dim irregularly, but data from historical photographic plates suggests that its overall brightness has also been gradually fading over the past century, a long-term trend that is even harder to explain. Furthermore, astronomers have now identified other stars with similarly extreme and irregular dimming patterns, such as the star known as EPIC 2445-12354, which experienced a single monstrous dip of 80%, a near-total eclipse of the star. The discovery of these siblings to Boyajian star suggests that whatever process is at work, it may not be a one-in-a-galaxy fluke, but a new, poorly understood phase of stellar evolution or a type of cosmic environment we are only beginning to recognize. The most recent studies have tilted the scales back toward natural, if still extraordinary, explanations. Detailed analysis of the star's light during dimming events has shown that different colors of light are blocked to different degrees. This chromatic effect is a crucial clue. A solid object like a planet or a megastructure would block all wavelengths of light equally. The fact that some colors are dimmed more than others strongly suggests that the material blocking the light is composed of fine dust particles. This points back to a natural origin, like the breakup of a giant planet or moon, creating an enormous cloud of debris that periodically drifts in front of the star. However, the exact source of this immense amount of dust and the mechanism that keeps it in such an irregular configuration remain active and fascinating areas of research. The enduring legacy of Boyajian star is not that it proved to be evidence of aliens, but that it perfectly exemplifies how modern astronomy tackles a true mystery. It began with a curious signal from a crowd-sourced project, which led to a rigorous process of proposing and testing hypotheses, from swarms of comets to cosmic dust clouds. Each proposed solution has been scrutinized, pushing our observational capabilities to their limits. The star has forced us to refine our ideas about what is possible in planetary systems and has opened our eyes to the potential for extreme variability in stars. It stands as a powerful reminder that the universe is under no obligation to conform to our expectations, and that sometimes the most valuable discoveries are not the answers we find, but the better questions we are forced to ask. While the mystery of Boyajian star presents a puzzle on the scale of a single solar system, our next discovery paints a picture of grandeur on a truly galactic scale. Venturing into the chaotic heart of our own Milky Way, astronomers have uncovered a structure so whimsically shaped it seems almost playful, a vast emission nebula that bears an uncanny resemblance to a giant cosmic candy cane. This festive-looking formation, officially known as G0.216-0.16, is not just a celestial curiosity. It is a vibrant and complex laboratory, revealing the powerful and often violent forces that sculpt the environment at the very center of our galaxy. Located approximately 27,000 light-years from Earth, this nebula is part of the tumultuous central molecular zone, a region brimming with intense radiation, powerful magnetic fields, and turbulent clouds of gas and dust. What makes the Candy Cane Nebula so striking is its distinct striped pattern. When observed in radio wavelengths, it displays alternating bands of bright and dark emission, creating a series of red and white swirls that coil through space. This banding is not a trick of light or an optical illusion. It is a direct result of a phenomenon known as synchrotron radiation. Here, electrons, accelerated to nearly the speed of light, spiral along powerful magnetic field lines. As they are forced into these curved paths, they release energy, which we detect as the nebula's glowing radio light. The alternating pattern arises from the intricate weave of these magnetic fields themselves, which are twisted and braided by the immense gravitational forces and energetic outflows present in the galactic center. The bright bands represent areas where our line of sight is aligned with the magnetic fields, allowing us to see the radiation more directly, while the dark bands are regions where the fields are oriented perpendicularly, minimizing the emission we can detect. The creation of such a precise structure in such a chaotic environment is a testament to the surprising order that can emerge from cosmic turmoil. The primary sculptor is thought to be the supermassive black hole at the very center of the Milky Way, Sagittarius, a star. While currently quiet, this black hole has likely experienced periods of intense activity in the past, spewing out jets of energy and matter. Combined with the powerful stellar winds from massive, young stars and the shockwaves from frequent supernova in the region, these forces compress and energize the vast clouds of molecular gas. This compression strengthens the local magnetic fields, organizing the chaos into the coherent, large-scale patterns we see. The candy cane is essentially a fossil record of this energetic activity, a lasting imprint of the dynamic processes that govern the most extreme regions of our galaxy. Studying this peculiar nebula provides astronomers with crucial insights that go far beyond its festive appearance. The striped pattern acts as a natural probe, allowing scientists to map the direction and strength of the magnetic fields in an area that is otherwise obscured by thick clouds of dust. Understanding these magnetic fields is key to solving some of the long-standing mysteries of the galactic center, such as how stars can form in an environment that is constantly being ripped apart by tidal forces and bathed in destructive radiation. The fields may provide a supportive scaffold, helping to channel and condense gas into dense cores that can eventually collapse to form new generations of stars. Furthermore, the nebula helps us understand the life cycle of energy in the galaxy. It demonstrates how the immense gravitational energy of the central black hole and the explosive energy of supernova can be transferred and transformed, ultimately manifesting as the intricate and beautiful structures that illuminate the galactic core. The cosmic candy cane is far more than a seasonal spectacle. It is a key to deciphering the complex and powerful language of magnetic forces that write the history of our galaxy. From the vibrant magnetic swirls at our galaxy's core, we now journey into a realm of profound darkness, to a discovery that is essentially the mirror image of the dark matter-free galaxy we encountered earlier. We arrive at the concept of a ghost, a cosmic phantom known as a dark galaxy. This is not a galaxy that is merely dim or far away. It is a hypothetical object made almost entirely of dark matter, with so few stars that it is virtually invisible. The very idea seems like a paradox. How can you have a galaxy without the galaxies? Yet, the hunt for these elusive entities is one of the most compelling endeavors in modern astronomy, and recent evidence suggests we may have finally found one, offering a potentially pure laboratory to study the mysterious substance that makes up the bulk of our universe. The story begins with a technique that has become a cornerstone of modern cosmology: gravitational lensing. According to Einstein's theory of general relativity, mass warps the fabric of spacetime. A massive object like a galaxy cluster can act as a cosmic lens, bending and magnifying the light from even more distant objects behind it. This effect allows astronomers to probe the distribution of mass within the lensing cluster itself. When they meticulously map this mass, they sometimes find a curious discrepancy: a concentrated clump of gravitational influence with no visible light to account for it. This is the primary signature of a potential dark galaxy, a massive gravitational anchor with no stellar city to justify its weight. One of the strongest candidates to date emerged from observations of the galaxy cluster Able 2626. Here, astronomers detected a significant gravitational lensing effect that pointed to a dense, compact object. But when they trained their telescopes on that precise location, they found nothing. No swirling spiral arms, no glowing elliptical haze, not even a faint smudge of stars. There was only the unmistakable pull of gravity, a ghost in the cosmic machine. Confirming such a discovery requires more than just a single observation. To build a compelling case, astronomers turn to a different method, one that listens to the faint radio whispers of the universe's most primitive gas, neutral hydrogen. This cold, diffuse gas is the raw material from which stars are born. Using colossal radio telescope arrays, scientists can map the distribution of this hydrogen across the sky by detecting the faint spectral line it emits. In several instances, they have found clouds of neutral hydrogen that are rotating in a way that indicates they are bound together by a significant amount of gravity, enough gravity to form a dwarf galaxy. The perplexing part is that these rotating gas clouds, which have names like HI1225+01, appear to contain no stars whatsoever. They are dark, starless halos of gas, seemingly held together by the gravitational glue of dark matter. The rotation speed of the gas is the key clue. It's far too fast to be explained by the gravity of the visible gas alone. Something unseen must be providing the additional gravitational pull to keep the cloud from simply flying apart. The existence of such dark galaxies, if confirmed, would be a monumental discovery with profound implications for our understanding of dark matter. First and foremost, it would provide perhaps the clearest evidence yet that dark matter is a real, physical substance that can coalesce into structures independently of normal matter. This would deal a significant blow to alternative theories of gravity, like modified Newtonian dynamics or MOND, which seek to explain galactic rotation curves by tweaking the laws of gravity rather than invoking an invisible substance. MOND struggles to explain how a cloud of gas could exhibit the rotation speeds of a galaxy without the presence of a massive dark matter halo. A bona fide dark galaxy would be a system where the modified gravity theory would have to work exceptionally hard to account for the observed motions without any visible mass to trigger the modification. Furthermore, dark galaxies could solve a long-standing problem in cosmology known as the missing satellites problem. Our best simulations of the lambda-cold dark matter model predict that large galaxies like the Milky Way should be surrounded by thousands of small dwarf satellite galaxies. Yet we have only observed a few dozen. Where are all the others? Dark galaxies offer an elegant solution. They are the missing satellites. They are there all around us, but they fail to form stars. This failure could have occurred for a variety of reasons. Perhaps the gas within them was too turbulent, preventing it from cooling and collapsing into stars. Maybe it was stripped away by the tidal forces of the larger host galaxy early in its history. Or perhaps the dark matter halo itself had a property, a specific density or formation history, that was simply unconducive to star formation. Finding these dark galaxies would not only fill a gap in our observational count, but would also teach us about the conditions necessary for turning primordial gas into the shining stars we see today. The quest to find these cosmic phantoms is far from over. Each candidate must be scrutinized to rule out other possibilities. Could the lensing effect be caused by a more mundane object, like a faint, ultra-diffuse galaxy that is just below the detection limit of our current telescopes? Is the rotating hydrogen cloud truly isolated, or is it just a tidal tail, a stream of gas ripped from a visible galaxy during a past interaction? New telescopes like the Vera see. Rubin Observatory are poised to revolutionize this search by imaging the entire sky with unprecedented depth, potentially revealing the faintest stellar glow associated with these dark matter halos or confirming their absolute blackness. The hunt for dark galaxies is a pursuit of the ultimate negative space, a search for the invisible scaffolding of the universe itself. By studying these ghosts, we are not just looking for something that isn't there. We are learning to see the universe in a fundamentally new way, through the subtle but undeniable influence of its most dominant yet secretive component. Just when we think we have a handle on the graceful choreography of solar systems, the universe throws us a curveball in the form of a planet that seems to be dancing to an entirely different tune. Our next discovery takes us to a world with a profoundly rebellious orbit, a gas giant known as HATP-7b. This isn't just a planet with a slightly tilted orbit. It is a world that orbits its star in the exact opposite direction of the star's own spin. Imagine a solar system where all the planets, like obedient children, run around their parent star in the same direction the star is turning. Now, picture one child deciding to run full speed in the opposite direction against the flow of all the others. This is the essence of a retrograde orbit, and its existence deals a direct blow to our standard models of how planetary systems are born. The story of planetary formation is one of a spinning, flattening disk. It begins with a vast cloud of gas and dust collapsing under its own gravity. As it collapses, it spins faster, much like a figure skater pulling in their arms. This motion flattens the cloud into a protoplanetary disk, a spinning pancake of material where the star forms at the center and planets coalesce from the surrounding material. Because all this material is moving in the same direction, the natural outcome is for the newborn star to spin in one direction and for the planets to orbit in that same plane and direction. It's a tidy, predictable process. HRTP-7b, with its backwards orbit, is the glaring exception to this rule. Its very presence is a flag planted in the ground, declaring that the history of its solar system was anything but tidy and predictable. Astronomers have proposed several dramatic mechanisms to explain how a planet could end up on such a path of cosmic rebellion. The most violent and likely scenario is a gravitational showdown known as planetary scattering. In a young, crowded solar system, multiple giant planets may form relatively close to one another. Their orbits can be unstable, and over millions of years, their mutual gravitational pulls can perturb each other, leading to a game of gravitational pinball. In this chaotic dance, one planet might be flung inward toward the star, while another is ejected out into the cold depths of interstellar space. For the planet flung inward, its orbit can be drastically altered, tilted, and even flipped entirely, resulting in the retrograde orbit we observe. This theory suggests that HRTP-7b is a survivor of a period of extreme instability, a lone giant that managed to cling to an orbit after a violent encounter sent it spinning backwards. A more subtle but equally fascinating explanation involves a distant gravitational puppet master and a phenomenon called the Kozai mechanism. This requires the presence of a second, more distant object, another star or a massive planet, whose gravity tugs on the inner planet over vast timescales. This gravitational influence can cause a slow, rhythmic exchange between the planet's orbital tilt and its eccentricity. Essentially, the orbit can be pumped up to become more and more elongated and tilted, until it eventually flips over entirely, settling into a stable but retrograde path. This process is like slowly twisting a hula hoop around your body until it's spinning in the opposite direction. It doesn't require a direct, violent collision, but rather a persistent, gentle nudge from a faraway companion that orchestrates the entire flip over millions of years. The discovery of such backwards orbiting planets has forced astronomers to actively search for these hidden perturbing bodies, turning single-star systems into potential binaries in our models. The implications of this discovery extend far beyond a single misbehaving world. It fundamentally challenges the idea that planetary systems are generally calm and orderly places. The existence of HRTP-7b and other retrograde planets like WRSP-17b suggests that gravitational chaos may be a common, if not essential, phase in the life of many solar systems. Our own solar system, with its well-behaved planets orbiting in a flat plane, might be the exception rather than the rule. This forces us to reconsider the typical narrative of planetary formation, adding a new chapter of dynamical instability that can completely reshape a system's architecture long after the planets have formed. These rebellious worlds are more than just orbital oddities. They are cosmic historians, their paths preserving the record of gravitational interactions that would otherwise be lost to time. They remind us that the serene stability we enjoy in our own cosmic neighborhood may be the product of a remarkably peaceful history, a luxury not shared by countless other systems across the galaxy. Moving from the rebellious orbits of rogue planets, we encounter a stellar death that occurred in the most isolated of circumstances, a cosmic explosion with no apparent home. In the vast, dark expanses that separate the great islands of galaxies, astronomers witnessed the unthinkable, a supernova detonating in what appeared to be the middle of nowhere. This was not a star dying within the bustling spiral arms of a galaxy, or even in the sparse outskirts of a galactic halo. This intergalactic supernova, with the catalog name of SN 2014J, erupted in profound emptiness millions of light years from the nearest large galaxy. Its location is a mystery that challenges our understanding of where stars can live and die, suggesting that the space between galaxies is not as barren as we once believed. There are two leading theories to explain this lonely cosmic blast, each one revealing a different aspect of galactic violence. The first and perhaps most dramatic possibility is that this supernova was the final, brilliant act of a rogue star, a massive sun that was violently evicted from its home galaxy. This stellar ejection is a real phenomenon, often the result of a gravitational slingshot effect within a dense star cluster, or more commonly, from the immense gravitational forces at play when two galaxies interact. When a star passes too close to a binary system of black holes or neutron stars at a galaxy's core, it can be flung outward at tremendous speeds, becoming a hypervelocity star. This stellar outcast would then spend the rest of its life traveling through the intergalactic void, a lone wanderer carrying the seed of its own destruction within its core. When its fuel was finally exhausted, it would explode in total isolation, its light the only testament to its long journey away from the stellar community of its birth. This theory paints a poignant picture of a star living and dying in exile, its spectacular death visible across the cosmos but witnessed by no neighboring worlds. The second compelling theory offers a different kind of mystery, suggesting that the space between galaxies is not entirely empty of structures but filled with ghosts. This supernova may not have been lonely at all, but rather the demise of a star within an invisible city, a dark galaxy. As we discussed earlier, these are hypothetical galaxies made almost entirely of dark matter, with very few stars, making them exceedingly difficult to detect. If such a dark galaxy existed in the vicinity of the supernova, it would provide the necessary host for the exploding star. The supernova's brilliant flash would then act as a temporary flare, illuminating this otherwise invisible realm for a brief moment. This scenario is incredibly exciting for astronomers, as it suggests a method for probing these elusive dark matter halos. The light from the supernova could be analyzed to determine the composition of the star that exploded, offering a rare glimpse into the stellar population of a galaxy we cannot directly see. It raises the tantalizing possibility that the cosmic web is not just defined by the bright galaxies we observe, but by a vast, unseen infrastructure of dark galaxies, each potentially harboring a small number of stars whose deaths serve as fleeting signals of their hidden existence. The implications of this intergalactic supernova stretch far beyond this single event. It forces a re-evaluation of the intergalactic medium, the space between galaxies. We can no longer think of it as a complete vacuum. Instead, it must be populated by a diaspora of rogue stars cast out from their galactic homes by gravitational interactions. Estimates suggest that there could be trillions of such stars adrift in the voids between galaxies, forming a faint, pervasive background glow known as intracluster light. Furthermore, the possibility of dark galaxies suggests that star formation can occur in the most unexpected places, in halos of dark matter that have managed to retain just enough gas to birth a generation of stars, even without the full complement of material found in a major galaxy. This lonely supernova is therefore a beacon, illuminating not just the empty space around it, but a whole new frontier of astronomical inquiry. It shows us that the universe is full of wanderers and ghosts, and that a star's final message can reveal secrets about the darkest and most isolated corners of the cosmos. From the solitary death of a star in the void, we turn now to a celestial object that seems to pulse with a strange, almost biological rhythm. In the constellation of Taurus, a pulsar known as B0933+02 has been observed doing something no other pulsar has been seen to do so clearly. It appears to be breathing. This isn't a literal intake of air, of course, but a remarkable periodic change in its behavior. Over a cycle of roughly 220 days, its rotation rate subtly speeds up and slows down, while the intensity of its lighthouse-like beam waxes and wanes. This rhythmic variation is so steady and predictable that it resembles the inhale and exhale of a living creature, presenting a puzzle that challenges our understanding of the most precise timekeepers in the universe. The constant, rapid-fire ticking of a pulsar is one of the most reliable phenomena in nature. These spinning neutron stars are the ultra-dense remnants of supernova explosions, and their rotational period is famously stable, changing only by infinitesimal amounts over centuries. This is why they are used as cosmic clocks for experiments in fundamental physics. The breathing of B0933+02 is therefore a profound anomaly. It's as if a perfectly engineered atomic clock suddenly developed a gentle, rhythmic sway in its tempo for no apparent reason. Astronomers had to rule out more mundane explanations, such as the gravitational tug of an orbiting planet, but the signal didn't fit that profile. This pointed to something intrinsic to the pulsar itself, an internal or environmental change that was modulating its spin and its power. One of the leading theories to explain this strange cadence involves a phenomenon known as free precession. Imagine a spinning top just as it starts to wind down. It doesn't just fall over, it often begins to wobble, its axis of rotation slowly tracing a circle in the air. This wobble is called precession. A neutron star, despite its incredible density, is not a perfectly rigid sphere. It has a crust of iron nuclei locked in a crystalline lattice surrounding a superfluid core. If this crust has a slight deformity, a mountain range a few millimeters high, for instance, the neutron star can experience free precession, wobbling on its axis as it spins. This wobble would slowly change the angle at which its powerful beams sweep across Earth. As the star precesses, we might see the beam more directly during part of the cycle, making it appear brighter, and then more edge-on, making it dimmer. Simultaneously, the wobble could cause slight changes in the star's moment of inertia, leading to the observed minute variations in its spin rate. In this model, the pulsar's breath is the slow, rhythmic wobble of a colossal, imperfect sphere. A second, equally compelling hypothesis suggests an external cause. The pulsar may be interacting with a fossil disk of debris. This idea proposes that after the supernova that created the neutron star, not all of the stellar material was blasted away. A small amount of debris could have fallen back, settling into an orbiting disk of gas and dust around the pulsar, much like the rings of Saturn but on a cosmic scale. As the pulsar spins, its powerful magnetic field and intense radiation would normally blow such a disk away. However, if the disk is just dense enough and at just the right distance, a delicate balance could be achieved. In this scenario, the inhale part of the cycle could correspond to a period when the disk drifts slightly closer to the pulsar. Its gravitational influence would transfer angular momentum to the star, causing it to spin up slightly. The increased radiation pressure from the pulsar would then push the disk back outward, leading to the exhale phase where the spin slows down again. This cyclical interaction would create the steady, long-period rhythm we observe, a cosmic dance between the dead star and the remnants of its former self. The implications of this discovery are significant, regardless of which theory proves correct. If it is free precession, it provides a unique window into the internal structure and rigidity of neutron stars, allowing us to probe the properties of matter under conditions of gravity and pressure that are impossible to replicate on Earth. We could learn about the star's elasticity and the possible existence of those tiny mountains on an otherwise perfectly smooth surface. If the cause is a debris disk, it challenges the assumption that pulsars are always surrounded by a perfect vacuum, suggesting that some can retain a tangible connection to their explosive past. It would also demonstrate a new way for a pulsar to exchange energy with its environment, a process that could be more common than we think. The breathing pulsar stands as a testament to the dynamic nature of even the most seemingly stable objects in the cosmos, reminding us that there are always new layers of complexity to uncover, revealing a universe that is never truly still or silent. But just as we chart the vast structures of the cosmos, we find that our own galaxy holds a secret at its very edge, a discovery that reveals a fundamental gap in our understanding of how galaxies interact with the space around them. Our journey now takes us to the outermost frontier of the Milky Way, to a place where a mysterious and invisible shield appears to be in place. Astronomers have recently mapped the distribution of cosmic rays, high-energy particles that race across the universe at nearly the speed of light, and found something deeply perplexing. According to all existing models, the density of these cosmic rays should be fairly uniform throughout the galactic disk and even increase as you move toward the outer reaches, where the protective magnetic fields of the inner galaxy are weaker. Instead, the data shows a sharp and unexpected drop-off. It's as if the Milky Way has built a vast, invisible wall at its perimeter, a barrier that actively prevents these energetic particles from the wider universe from flowing inward. This is not a solid structure, but a phenomenon, a region where the rules of particle physics seem to change in ways we cannot yet explain. The primary suspect for creating this cosmic barrier is the galaxy's own magnetic field. We've long known that the Milky Way is wrapped in a giant, albeit diffuse, magnetic halo. The leading theory suggests that out in the galactic hinterlands, this magnetic field could be amplified or contorted into a kind of magnetic mirror. As cosmic rays, which are charged particles, approach this region, the converging magnetic field lines would deflect them, bouncing them back like a ball thrown against a wall. This would create an effective boundary, shielding the inner galaxy from the full brunt of external cosmic radiation. However, for this to work as effectively as the observations suggest, the magnetic field at the edge would need to be far stronger and more organized than our current models predict. This forces a dramatic re-evaluation of the strength and structure of our galaxy's magnetic halo, suggesting it plays a much more active and powerful role in shaping our galactic environment than we ever realized. A second, equally compelling hypothesis points to the collective power of stellar winds. The outer disk of the Milky Way, while less densely packed with stars than the center, is still a region of active star formation. Massive, young stars in these areas generate powerful winds, continuous outflows of charged particles that stream out into space. The combined effect of countless such stellar winds could create a persistent, galaxy-wide wind of its own flowing outward from the disk. This outflow would act as a counterforce against incoming cosmic rays, effectively pushing them back and preventing their easy entry. Imagine it as our galaxy having its own weather system, with a steady breeze blowing from the inside out, holding back an external storm of particles. This idea beautifully links large-scale galactic dynamics to local stellar activity, but it also presents a challenge. The energy required to sustain a wind powerful enough to hold back high-energy cosmic rays across such a vast scale is immense, and it's not clear if the star-forming regions in the galactic fringe are numerous enough to generate it. The existence of this barrier creates a significant challenge for our models of galactic evolution and cosmic ray propagation. Cosmic rays are not just a curiosity, they are a fundamental component of the interstellar medium, influencing everything from the chemistry of gas clouds to the potential for life on planets. They provide pressure that helps support gas clouds against gravitational collapse, and they can even catalyze the formation of complex molecules. A galaxy that selectively filters these particles is managing its own internal energy budget in a way we hadn't anticipated. This discovery suggests that galaxies are not passive collections of stars. They are dynamic ecosystems that can regulate their own internal environment. The Milky Way's invisible shield might be a key mechanism for maintaining the delicate conditions necessary for steady star formation and planetary development, effectively creating a more stable habitat within its borders. This finding forces us to see our galaxy not just as a structure in space, but as an active participant in a complex cosmic dialogue, one that is still speaking in mysteries we are only beginning to hear. While some cosmic outcasts are born from the violent interactions of binary stars, others are forged in the most extreme gravitational crucible imaginable, the very heart of our galaxy. Our next oddity is a stellar cannonball, a runaway star known as a hypervelocity star, hurtling through the Milky Way's halo at speeds so great they defy the very pull of our galaxy's gravity. These are not merely fast-moving stars, they are celestial projectiles traveling at over 1,000 kilometers per second, a velocity so immense that they are destined for one ultimate fate: to escape the Milky Way entirely and spend eternity wandering the frigid, intergalactic void. The story of how a star can achieve such an incredible speed is a tale of cosmic pinball on the grandest scale. The most widely accepted theory points directly to the supermassive black hole that lurks at the center of our galaxy, Sagittarius, a star. Imagine a binary star system, two suns orbiting one another, that ventures too close to this gravitational monster. The black hole's immense tidal forces can violently tear the binary pair apart. In a process known as the Hill's mechanism, one star is captured into a tight orbit around the black hole, while its companion is flung away at a phenomenal velocity. It's a gravitational slingshot effect, but one where the sling is the most destructive object in the galaxy. The energy for this incredible launch comes from the orbital energy of the binary system itself, with the black hole acting as a cosmic catalyst, transferring that energy into a single, spectacular ejection. Tracking the trajectory of these runaway stars is like reading a cosmic receipt from the event that created them. By carefully measuring a hypervelocity star's path across the sky and its Doppler shift, astronomers can trace a line backward through the galaxy. In several confirmed cases, that line points directly back to the galactic center, providing compelling evidence for the black hole ejection theory. But these stars are more than just products of a violent past. They are invaluable tools for probing the present. As a hypervelocity star races outward from the core, it passes through the diffuse halo of dark matter that envelops the Milky Way. The precise shape of its trajectory is subtly influenced by the gravitational pull of this invisible material. By studying the paths of multiple such stars, astronomers can essentially map the distribution and density of dark matter in our galaxy's halo, using these natural probes to illuminate the unseen structure that binds our galaxy together. The existence of hypervelocity stars reveals a dynamic and sometimes violent ecosystem at the galactic center. It suggests that binary star systems are common in that tumultuous region, and that close encounters with Sagittarius, a star, are a regular occurrence over cosmic timescales. Each runaway star we detect is a fossil record of a dramatic gravitational interaction that occurred millions of years ago. Its journey a permanent testament to the destructive power that can also, paradoxically, create a new class of celestial wanderer. These stellar exiles offer a unique perspective on our galaxy, proving that its gravity is not an inescapable prison, but a force that can, under the most extreme circumstances, be harnessed to send its very own suns on a one-way trip into the great unknown. Moving from the explosive chaos of stellar ejections, we find a marvel of gravitational harmony in a distant star system, where planetary moons defy conventional expectations. Astronomers studying the data from powerful telescopes have uncovered evidence for a configuration that was long thought to be theoretically possible but incredibly rare. A gas giant exoplanet that is host to multiple large moons, all sharing the same orbital path. Imagine not a single moon like our own, but a family of moons traveling around their planet like cars on a cosmic racetrack, perfectly spaced and maintaining a delicate gravitational balance. These are co-orbital moons, and their existence in a stable system presents a fascinating challenge to our understanding of how celestial bodies form and coexist. The dynamics of such a system hinge on a concept known as a Lagrangian point. In any two-body system, like a planet and a star, there are 5 specific points where the gravitational pull of the two large bodies balances with the centrifugal force felt by a smaller, third object. The most stable of these are the L4 and L5 points, which lie 60 degrees ahead of and behind the smaller body in its orbit. In the case of a giant planet, these points become gravitational safe havens where material can accumulate. Instead of a single moon forming in a lone orbit, multiple moonlets could coalesce in these stable zones, leading to a situation where several sizable moons share the same orbital radius around their host planet. They don't collide because they are locked into a gravitational dance, each one occupying its own designated position within the orbital lane, perpetually leading or trailing their sibling moons in a stable configuration. This discovery pushes the limits of moon formation theories. The dominant model for large moons, based on our own solar system, suggests they form from a circumplanetary disk, a ring of gas and dust that surrounds a young planet, similar to the protoplanetary disk around a star. In this scenario, moons coalesce at different distances from the planet, each carving out its own distinct orbit. A system of co-orbital moons, however, suggests a much more chaotic and dynamic past. It is unlikely that multiple large moons could form in the same narrow band from a calm disk without immediately destabilizing each other. A more probable explanation is that these moons did not form in their current positions at all. They may have been born farther out in the system and then migrated inward, becoming captured into this resonant configuration through a complex series of gravitational interactions. Alternatively, a single large moon could have suffered a catastrophic collision with another object, with the resulting debris slowly coalescing into several smaller moons that were naturally shepherded into the stable Lagrangian points. The long-term stability of such a system is a delicate puzzle. While Lagrangian points are theoretically stable, the presence of multiple massive bodies introduces perturbations that could, over millions of years, lead to collisions or ejections. The fact that we observe this system means it has found a way to persist. This likely involves a precise ratio of masses and distances, a gravitational harmony where the moons gently tug on each other in a way that reinforces their positions rather than disrupting them. It's a celestial rhythm more complex than a simple duet, a gravitational symphony where each moon's motion is precisely tuned to the others. Studying this system provides a unique natural laboratory for testing the limits of orbital mechanics, offering insights that could explain the arrangement of asteroids in our own solar system's Jupiter Trojans, which occupy the Sun-Jupiter L4 and L5 points, but on a much smaller scale. The implications of this oddity extend beyond a single exotic system. If co-orbital moons are possible, it dramatically expands the potential diversity of planetary systems in our galaxy. It suggests that moons, which are prime candidates in the search for habitable environments, might not always be solitary worlds. A system with multiple large, co-orbiting moons could create a complex and dynamic environment, with tidal forces and reflected light creating unique conditions on their surfaces. Finding such a configuration forces astronomers to refine their models of planetary system formation, acknowledging that the peaceful, orderly process we see in our solar system is just one possible outcome. The universe, it seems, has a flair for creating intricate gravitational ballets where multiple partners can share the stage in a stable, if precarious, dance. Even the most powerful lights in the universe must eventually go out, but as we're learning, their glow can linger in the cosmos like a ghostly whisper long after the source has faded to black. This brings us to our 19th oddity, a celestial phantom discovered not by the light it emits now, but by the echo of its ancient brilliance. Astronomers have identified a vast, faint cloud of ionized gas, stretching for hundreds of thousands of light years, that hangs in the darkness with no apparent power source. The leading theory is that we are witnessing the ghost of a dead quasar, the final, fading afterglow of an object that once dominated its corner of the universe with unimaginable ferocity. To understand what we're seeing, we need to recall what a quasar is. At the heart of many young galaxies sits a supermassive black hole. When this black hole is actively feeding on vast quantities of gas, dust, and even stars, the material doesn't fall in silently. It forms a superheated, swirling accretion disk that shines with the brightness of 1 trillion suns, outshining the entire galaxy that hosts it. This is a quasar, the most luminous and energetic engine in the cosmos. But quasars are not eternal, they are a phase. Eventually, the black hole consumes the available fuel, the accretion disk dwindles, and the brilliant beacon shuts down, leaving behind a quiet, dormant giant. What makes this particular discovery so extraordinary is that it captures the aftermath of this shutdown process. The immense cloud of gas we see was blasted and ionized, its atoms stripped of their electrons, by the quasar's intense radiation when it was active. Now, millions of years after the quasar has fallen silent, that gas is still glowing faintly as it slowly recombines, a fossilized sphere of light preserving the memory of the eruption. The process at work here is a cosmic version of a light echo. Imagine standing in a vast, dark cave and shouting. The sound travels out, hits the walls, and a moment later you hear the echo return. Now replace the shout with a flash of light and the cave walls with a gigantic cloud of interstellar gas. When the quasar flashed into existence, its light rushed outward at, well, the speed of light. The initial flash is long gone, having passed our planet millions of years ago. But that light also struck the surrounding clouds of gas that were floating far from the galactic center. The energy from that light excited the gas, causing it to glow. We are now seeing that delayed glow, the echo of the original flash as it reverberates through the cloud. The incredible size of the cloud means that light from different parts of it reaches us at different times, allowing us to effectively see the aftermath of the quasar's activity stretched out over an immense volume of space and time. Studying this ghostly cloud is like having a time machine that allows us to read the biography of a quasar. By analyzing the spectrum of the faint light, breaking it down into its constituent colors, astronomers can determine the composition of the gas and, crucially, the nature of the radiation that ionized it. This tells us what the quasar was like in its final, active phase. Was it a steady, brilliant beacon, or did it flare up in violent, intermittent outbursts? The structure of the cloud holds clues to these questions. Furthermore, the mere existence of such a large and coherent structure tells a story about the environment around the quasar. It suggests that the ancient galaxy was surrounded by an extensive halo of pristine gas, which was then sculpted and illuminated by the central engine's powerful winds and radiation. This discovery profoundly impacts our understanding of galactic evolution. Quasars are not just cosmic curiosities, they are thought to play a critical role in regulating the growth of their host galaxies. The intense radiation and powerful jets they emit can blow away vast reservoirs of star-forming gas, effectively shutting down star birth in a process called quasar feedback. The ghost cloud serves as tangible evidence of this feedback mechanism in action. It shows us the very material that was pushed away and heated by the quasar's energy, providing a direct link between the death of the active nucleus and the future evolution of the galaxy. By finding and studying more of these quasar ghosts, we can begin to understand how common this regulatory process is, and how the violent deaths of these brilliant beacons ultimately shape the galaxies we see in the universe today, including our own. While most of the cosmic oddities we've explored are defined by their location or their bizarre behavior, our 20th discovery reminds us that sometimes the most profound mysteries are simply passing through. In 2017, astronomers in Hawaii detected a faint, fast-moving object unlike any other. It was not bound by the sun's gravity, but was instead racing through our solar system on a hyperbolic trajectory, a visitor from the depths of interstellar space. They named it Oumuamua, a Hawaiian word meaning scout from the distant past. This was the first time humanity had ever laid eyes on an object born around another star, and its peculiarities would launch a scientific debate that continues to this day. The initial puzzle of Oumuamua was its shape. Based on the dramatic way its brightness changed as it tumbled through space, astronomers deduced that it was highly elongated, perhaps 10 times as long as it was wide. This made it unlike any asteroid or comet we have seen in our own solar system, where such extreme proportions are unheard of. Compounding the mystery was its motion. As Oumuamua sped away from the sun, it exhibited a tiny but undeniable acceleration that could not be explained by gravity alone. For a comet, this would be simple. Sunlight heats frozen ices on its surface, causing them to vaporize and jet out, acting like a small rocket engine. But Oumuamua showed no visible coma, the cloud of gas and dust that surrounds a comet's nucleus. It appeared as a sterile, inert rock, yet something was pushing it. This non-gravitational acceleration fueled intense speculation, with explanations ranging from the release of hidden hydrogen ice to the more sensational possibility that it was an artificial light sail from an alien civilization. The more likely, yet still fascinating, explanations paint a picture of a truly exotic object. One compelling idea is that Oumuamua is a fractal-like aggregate of dust, a dust bunny, formed in the outer reaches of a distant planetary system. Its porous structure could have allowed solar radiation pressure to push on it effectively, accounting for the acceleration without the need for visible outgassing. Another theory suggests it is a shard of a Pluto-like planet that was torn apart by its parent star, a piece of nitrogen ice that gradually eroded away during its long journey, explaining its strange acceleration and lack of a tail. What makes Oumuamua so important is that it provides our first physical sample of another solar system. Its very existence tells us that planetary systems are constantly ejecting material into the galactic void, and that our cosmic neighborhood is likely filled with such silent, tumbling travelers. Just 2 years after Oumuamua's brief visit, a second interstellar object was discovered, and it provided a crucial point of comparison. Named 2I/Borisov after its amateur astronomer discoverer, this visitor was immediately recognizable as a comet. It displayed a prominent coma and a faint tail, its ices vaporizing furiously as it swung near the sun. Unlike the enigmatic Oumuamua, Borisov was comfortingly familiar. Analysis of its light revealed a composition rich in carbon monoxide, a signature that was distinct from most comets in our solar system. This key difference is a treasure trove of information. It suggests that Borisov formed in an extremely cold environment, far from its host star, much colder than the region where our own Oort cloud comets originated. The fact that these two visitors are so different from each other is perhaps the most significant finding of all. It demonstrates a stunning diversity in the building blocks and formation histories of other planetary systems. We have now sampled two, and they are nothing alike, hinting at a galaxy filled with a wild variety of planetary architectures and evolutionary paths. The detection of these interstellar interlopers has fundamentally changed our perspective. We now know that our solar system is not an isolated island. It is part of a dynamic galactic ecosystem, constantly exchanging material with its stellar neighbors. This opens up an entirely new field of astronomy. Upcoming observatories like the Vera C. Rubin Observatory are expected to find many more of these visitors each year. With a larger sample, we will be able to move from puzzling over individual anomalies to understanding the population statistics of interstellar objects. Are most like Borisov or like Oumuamua? Do they carry the water and organic materials that are essential for life as we know it? Each new visitor will be a piece of a grand puzzle, helping us to build a composite picture of how planets form and evolve throughout the Milky Way. These silent scouts from distant stars are therefore not just curiosities. They are messengers carrying with them the secrets of their alien homes and offering us a glimpse into the cosmic processes that shape worlds far beyond our own. For decades, astronomers have known that our Milky Way galaxy is not simply drifting aimlessly through the cosmos. Along with our local group of galaxies, we are all caught in a vast, unseen river of motion, flowing toward a specific point in the sky near the constellation Centaurus at a staggering 1.5 million miles per hour. The source of this immense gravitational pull is known as the Great Attractor, a name that perfectly captures both its function and its profound mystery. It represents a gravitational anomaly of such scale that it must be caused by a concentration of mass equivalent to tens of thousands of Milky Ways. Yet, for years, the Great Attractor remained frustratingly hidden from our view, lying in what astronomers call the zone of avoidance, a region of the sky obscured by the dense gas and dust of our own galaxy's central plane. It was like trying to see a distant mountain range through a thick, perpetual fog. But recent technological breakthroughs are finally parting that cosmic curtain, offering new clues about what lies at the end of our galactic journey. The key to unraveling this mystery has been the ability to peer through the obscuring dust using wavelengths of light that can penetrate it, specifically infrared and radio waves. Projects like the 2-micron All-Sky Survey, or 2MASS, have meticulously mapped the sky in infrared light, which slips past the dust clouds that block visible light. Meanwhile, radio telescopes have charted the motions of hydrogen gas in galaxies behind the zone, allowing astronomers to infer their distances and velocities. By combining these new datasets, scientists have been able to construct a three-dimensional map of our cosmic neighborhood on a scale never before possible. This monumental effort led to the groundbreaking identification of the Laniakea supercluster, a Hawaiian word meaning immeasurable heaven. Laniakea is our true cosmic address, a vast filamentary network of over 100,000 galaxies spanning 500 million light-years, and the Great Attractor is not its final destination, but rather a central gravitational valley within it. Think of Laniakea not as a simple sphere, but as a giant cosmic watershed. Just as water on a continent flows downhill into streams, then rivers, and finally into a central ocean, galaxies flow along gravitational pathways toward the Great Basin of the supercluster. The Great Attractor is the deepest point in that local basin, the gravitational equivalent of a low-lying plain toward which all the surrounding galactic rivers are flowing. Our Milky Way is like a single leaf caught in one of those rivers, moving with the current. The latest mapping efforts have revealed that the pull we feel is not from a single, unimaginably dense object, but from the combined gravitational influence of several massive galaxy clusters located in that region, most notably the Norma cluster. This cluster is itself incredibly dense, but it alone cannot account for the full strength of the attraction. The new clue that is solving the puzzle is the realization that there is even more mass hidden behind the Norma cluster, a structure known as the Vela supercluster, which was only confirmed in recent years. It appears the Great Attractor is not one thing, but a confluence of several immense structures, their combined gravity creating the powerful flow we observe. This new understanding fundamentally changes our place in the universe. We are not being pulled toward a mysterious, singular monster in the dark, but are instead participating in the grand, slow-motion choreography of the cosmic web on the largest scales. The gravitational tides that shape Laniakea are a direct result of the distribution of both visible matter and, more importantly, dark matter. The hidden mass concentration pulling us is essentially a massive knot in the dark matter web of the universe. By studying the flow of galaxies within Laniakea, astronomers are not just mapping stars, they are using the motions of visible galaxies as tracers to chart the invisible scaffolding of dark matter that dictates the large-scale structure of everything. The Great Attractor, once a profound enigma, is now a key piece of evidence in our quest to understand the hidden forces that have shaped the universe since the Big Bang, revealing that our journey is part of a cosmic dance billions of years in the making. But our catalogue of cosmic wanderers does not stop at interstellar asteroids and comets. Far beyond the reach of any star's warmth, in the profound and permanent night of interstellar space, another kind of rogue drifts, a planet utterly alone. Most planets are tethered to a star, bound by gravity to orbit a sun. But recent discoveries have confirmed the existence of rogue planets, worlds flung from their native solar systems by gravitational chaos to wander the galaxy as cosmic orphans. And one such planet, a Jupiter-sized giant known only by a catalogue number, has presented us with a breathtaking paradox. It is a world without a sun, a dark traveler in the void, yet it possesses a feature we associate with the vibrant interaction between a star and its planets, a brilliant, powerful aurora. On Earth, the northern and southern lights are a celestial ballet choreographed by our sun. The solar wind, a constant stream of charged particles, flows outward and interacts with our planet's magnetic field. This field funnels the particles toward the magnetic poles, where they collide with atoms in the upper atmosphere, causing them to glow in shimmering curtains of green, red, and purple. It's a beautiful phenomenon, but one entirely dependent on the energy provided by a parent star. So how can a planet untethered from any star, floating in the near-total vacuum of interstellar space, possibly generate an aurora? The answer lies not in a stellar wind, but in a fascinating and unexpected relationship between the planet and its own moons. The primary mechanism powering this rogue planet's aurora is believed to be a process of tidal heating and volcanic activity, but on a scale that dwarfs anything in our solar system. While this planet has no star, it may not be entirely alone. Evidence suggests it could be accompanied by large, orbiting moons. As these moons travel around the planet, their gravitational pull flexes and stretches the planet's interior, much like the moon's gravity causes tides on Earth. However, for a gas giant, this gravitational interaction is far more intense. The constant tugging generates immense internal friction, heating the planet's core to extraordinary temperatures. This heat drives powerful volcanic activity on any solid moons, and more importantly, it energizes the planet itself, creating a tumultuous, electrically conductive environment within its deep atmospheric layers. This internal heat and motion are the key. Within the planet's vast, swirling atmosphere of hydrogen and helium, charged particles are abundant. The planet's rapid rotation, a common trait for gas giants combined with the convective heat rising from its tormented core, acts like a colossal dynamo. This natural dynamo effect generates a powerful magnetic field, one that may be even stronger than Jupiter's. Now, here is the crucial link. A large volcanic moon like Jupiter's Io would be a critical component. If this rogue planet has such a moon, the relentless tidal forces would cause it to be incredibly volcanically active, spewing vast quantities of ionized gas and dust into space. This material becomes trapped by the planet's powerful magnetic field, creating a dense, localized plasma torus, a ring of charged particles around the planet. The rotation of the planet's magnetic field then accelerates these particles, whipping them along magnetic field lines and slamming them into the planet's upper atmosphere at the poles, creating a permanent, dazzling auroral display entirely self-generated from within the system. The implications of this discovery are profound for our understanding of planetary science and the potential for habitability in the darkest corners of the galaxy. Firstly, it demonstrates that planetary magnetic fields can be sustained independently of a star. The energy comes from a combination of internal heat left over from formation and ongoing tidal heating, proving that planets can be dynamic, active worlds long after they are ejected from their stellar families. This redefines what it means to be a dead or frozen world. Secondly, and perhaps more excitingly, it opens up a new avenue for potential habitability. A rogue planet like this, heated from within by tidal forces and protected by a strong magnetic field from cosmic radiation, could potentially host a liquid water ocean beneath a thick, icy crust on one of its moons, much like Jupiter's moon Europa. The energy for life would not come from the light of a sun, but from the gravitational friction and internal warmth of the planet itself. This means the galaxy could be filled with dark, nomadic worlds unseen from Earth, each with the potential to harbor their own hidden, subsurface biospheres, thriving in the eternal night of interstellar space. For centuries, astronomers have mapped the universe by pinpointing the locations of stars and galaxies, the bright cities of the cosmos. But these luminous points are not scattered randomly. They are connected, arranged along vast, invisible threads that form the largest structure in existence, the cosmic web. This web is the fundamental architecture of the universe, a network of dark matter filaments that serves as a scaffolding upon which galaxies are built. While its existence has been a cornerstone of cosmological theory for decades, actually seeing it has been an immense challenge, like trying to map a spider's web in a dark room by only looking at the dewdrops clinging to its strands. Recently, however, a profound breakthrough has given us our first direct, large-scale image of this hidden framework, not by seeing the dark matter itself, but by capturing the faint, primordial glow of the hydrogen gas that has been drawn into its gravitational embrace. The key to this discovery was shifting our gaze from the brilliant dewdrops, the galaxies, to the space between them. Astronomers turned the powerful MUSE instrument on the Very Large Telescope in Chile toward a single patch of sky for over 140 hours, staring at a region containing thousands of distant galaxies. They weren't looking for the light from the galaxies, but for a specific, incredibly faint wavelength of ultraviolet light emitted by hydrogen gas. This particular emission, known as Lyman alpha radiation, is a fingerprint of the most abundant element in the universe. The immense sensitivity of the observation allowed them to detect this faint glow from the hydrogen that has been concentrated within the dark matter filaments of the cosmic web. The resulting image is nothing short of spectacular, a sprawling, wispy network of luminous tendrils connecting galaxies like pearls on a necklace and stretching across billions of light years. It is a ghostly map of the universe's underlying structure, a long-predicted blueprint finally brought into stunning reality. This direct observation is a monumental confirmation of the lambda cold dark matter model, our leading theory of cosmic evolution. According to this model, the universe began in a nearly smooth state after the Big Bang. Tiny quantum fluctuations in the primordial soup were amplified by gravity over billions of years. Dark matter, which responds only to gravity, clumped first, forming an invisible web, normal matter. The hydrogen gas was then pulled by gravity into these dark matter filaments, eventually cooling and condensing to form galaxies at the intersections where filaments crossed. Seeing the hydrogen gas tracing out the exact filamentary structure that simulations have predicted for years is like finding fossilized footprints that perfectly match the skeleton of a long-extinct animal. It provides tangible, visible proof that our basic understanding of how the universe grew from a featureless beginning into the complex tapestry we see today is fundamentally correct. Beyond mere confirmation, this new view of the cosmic web offers an unprecedented way to study the properties of dark matter itself. While dark matter remains invisible, its presence is undeniable in the shape and distribution of the glowing filaments. By analyzing the brightness and thickness of these hydrogen tendrils, astronomers can weigh them. The amount of visible hydrogen gas, however, is nowhere near enough to account for the gravitational pull needed to create such coherent, massive structures. The vast majority of the mass must be the dark matter that defines the filament's gravitational potential. This allows scientists to measure how dark matter is distributed along the web's threads, providing crucial clues about the nature of its mysterious particles. For instance, the fact that the filaments appear so well defined and narrow rather than puffy and diffuse supports the idea that dark matter is cold, meaning its particles move relatively slowly, allowing them to clump together efficiently on these large scales. The implications of this discovery extend to the very story of how galaxies are born. The images reveal that the filaments are not just passive roads, they are dynamic rivers of fuel. The faint glow shows that vast reservoirs of primordial hydrogen gas are flowing along these cosmic highways, channeled by gravity toward the growing clusters of galaxies at the nodes. This continuous inflow of fresh material is the lifeblood of galaxy formation, providing the raw fuel for new stars and sustaining the growth of galaxies over cosmic time. It helps explain why galaxies in dense clusters are often larger and more evolved than their isolated counterparts. They have access to a richer supply of gas delivered by multiple intersecting filaments. This direct observation of the web transforms our understanding of galaxy evolution from a theoretical concept into a visible process, allowing us to watch, in a sense, the universal system of nourishment that has built the galaxies we see today. This glowing map is more than a pretty picture. It is a living diagram of the universe's growth, a snapshot of the continuous cycle of construction that has been underway since the dawn of time. But the cosmic web is not the only place where we find intricate structures etched into the fabric of space. Sometimes these patterns appear on a much more intimate scale, revealing the final, dramatic chapters of a star's life. Our next discovery takes us to a stellar corpse that has adorned itself with a structure of breathtaking beauty and profound violence. Astronomers have identified a white dwarf star, the Earth-sized cinder of a sun-like star that is encircled by something never before seen, a vast, precise, spiral-shaped disk of debris. This isn't a random cloud of dust, it is a cosmic whirlpool, a pinwheel of doom swirling around a dead star, and its existence tells a terrifying and fascinating story about the ultimate fate of planetary systems. To understand the significance of this spiral, we must first appreciate the nature of a white dwarf. After a star like our Sun exhausts its nuclear fuel, it goes through a violent but brief phase as a red giant, swelling to engulf any inner planets. It then sheds its outer layers, leaving behind an incredibly dense white-hot core, a white dwarf. This remnant is so dense that a single teaspoon of its material would weigh as much as an elephant on Earth. For a long time, astronomers believed that the planetary systems around such stars would be completely obliterated or rendered inert. But recent observations have shown that many white dwarfs are surrounded by rings of dusty debris, the pulverized remains of asteroids, comets, and even planets that survived the red giant phase only to be torn apart by the white dwarf's immense gravity. What makes this particular white dwarf, known as SRO 20646, so extraordinary is that its debris is not in a simple ring. It has been sculpted into a magnificent spiral. The formation of this spiral is a direct result of gravitational chaos. The leading theory points to a surviving planet orbiting at a distance from the white dwarf. This planet, having escaped consumption during the red giant phase, now orbits the dead star in an eccentric or oval-shaped path. As it travels on this elongated orbit, its gravitational pull acts like a shepherd but a destructive one. It perturbs the orbits of countless smaller bodies, asteroids, and dwarf planets in the outer reaches of the system. These perturbations send a continuous stream of debris spiraling inward toward the white dwarf. However, the debris doesn't fall in a straight line. The combined gravity of the white dwarf and the perturbing planet imparts a shear force on the infalling material, stretching and smearing it out. Because the debris is arriving from different distances and at different speeds, this shearing effect organizes the dust into a distinct spiral arm. Much like stirring milk into coffee can create a temporary spiral pattern. The planet in this scenario is the spoon that stirs the cosmic cup, its orbit dictating the graceful yet deadly shape of the disk. This discovery provides a grim preview of our own solar system's distant future. Billions of years from now, our sun will become a red giant, likely consuming Mercury, Venus, and possibly Earth. What remains of our planetary system, the asteroid belt, Jupiter, Saturn, and the outer worlds, will be left orbiting the new white dwarf sun. The immense gravity of this stellar cinder will begin to wreak havoc. The gravitational balances that have held the system stable for eons will be disrupted. Asteroids and moons will be flung onto chaotic paths, colliding and breaking apart. The spiral disk around SO 200-646 shows us the likely result, a phase of absolute destruction where the remaining planets gravitationally shred the smaller bodies in the system, creating a final, beautiful, and lethal monument to a once thriving family of planets. We are essentially looking at a celestial graveyard where the arrangement of the dust spells out the cause of death. Beyond its narrative power, the spiral serves as a unique natural laboratory. The pattern itself allows astronomers to measure processes that are otherwise invisible. By studying the tightness of the spiral arms and their rate of rotation, scientists can indirectly weigh the white dwarf and estimate the mass and orbit of the perturbing planet that they cannot see directly. It's a form of gravitational detective work where the dust is the evidence. Furthermore, analyzing the light from the white dwarf as it passes through this spiral disk provides a spectroscopic fingerprint of the debris. This has revealed a startling fact. The dust is rich in heavy elements like oxygen, magnesium, and iron. This is profoundly important because a white dwarf's surface should be composed almost entirely of hydrogen and helium. Any heavier elements should sink into its ultra-dense interior almost immediately. The presence of these metals on the surface is direct evidence that the star is currently cannibalizing the rocky remains of its former planets. We are not just seeing the destruction, we are witnessing the act of consumption as the dead star feeds on the bones of its own children. The white dwarf with a spiral disk is more than just a pretty picture. It is a dynamic snapshot of a solar system in its final death throes. It connects the grand fate of a star to the intricate dynamics of its planetary companions, showing that even in death there is a complex gravitational ballet. This oddity provides a crucial link in our understanding of galactic chemical evolution, revealing how the heavy elements forged in stars and locked away in planets can be recycled back into the interstellar medium through such violent events. It is a stark and beautiful reminder that the cosmos is in a constant state of transformation, where the end of one story becomes the raw material for the next. Yet, even as we map the grand architecture of the cosmic web, we find that the universe still has a talent for placing things where they simply do not belong. Our next discovery confronts us with a galaxy that, according to our most sophisticated computer models of cosmic evolution, should not exist at all. In a vast, predicted void within the large-scale structure of the universe, a region that simulations showed should be a near-total emptiness for hundreds of millions of light-years, astronomers have found a lone, faint galaxy. It is a solitary island of stars adrift in a cosmic ocean that our maps declared to be a desert. This isn't just a minor discrepancy. It is a direct challenge to the lambda cold dark matter model, the very foundation of modern cosmology, suggesting that our virtual universe might be missing some key ingredients of reality. The lambda CDM model is our playbook for how the universe grew from a nearly smooth state after the Big Bang into the intricate cosmic web we observe today. It posits that the gravitational pull of cold, slow-moving dark matter acted as a scaffolding, first forming small clumps that then merged into larger and larger structures. The normal matter, the gas that makes stars and galaxies, simply followed this dark matter skeleton, pooling at the intersections of filaments to create galaxy clusters and collecting along the filaments themselves. The model has been incredibly successful, accurately predicting the properties of the cosmic microwave background and the large-scale distribution of galaxies. But it also makes a specific prediction about emptiness. It tells us where the voids should be and just how empty those voids ought to be. The galaxy in question sits squarely in one of these predicted voids, a region that, in the simulation, contains so little matter that a galaxy of its size should never have had the chance to form there. Its presence is like finding a bustling metropolis in the middle of the Sahara Desert, based on a geological survey that said the area lacked even the groundwater for a small village. So how did this galaxy come to be? Astronomers are exploring several compelling and potentially revolutionary explanations. The first possibility is that our galaxy formation physics within the simulations is incomplete. The process of turning primordial gas into stars is extraordinarily complex, involving turbulence, magnetic fields, and feedback from supernova factors that are difficult to model with perfect accuracy. It is possible that under certain rare conditions, a galaxy could form with far greater efficiency than we typically assume, requiring a much smaller seed of dark matter to get started. This lone galaxy could be a testament to a star-forming pathway we have not yet accounted for, a cosmic shortcut that allows islands of light to bloom in the darkest of places. A second, more profound possibility involves the very nature of dark matter. The standard model uses cold dark matter which clumps together efficiently. But some physicists propose alternatives such as warm dark matter, where the particles move at a significant fraction of the speed of light. Warm dark matter would suppress the formation of structure on small scales, leading to a different distribution of galaxies, potentially with more isolated galaxies in the void. The discovery of this lone galaxy could be a piece of evidence nudging us toward this alternative, implying that the dark matter particle has properties we have not yet imagined. Furthermore, the existence of such an outlier forces us to consider the role of cosmic randomness. Our universe is the result of quantum fluctuations inflated to cosmic proportions. Is it possible that this galaxy is simply a statistical fluke, a particularly large initial fluctuation that, against all odds, grew into a full-fledged galaxy in an otherwise empty neighborhood? If so, its discovery tells us that our universe might allow for more rare and extreme outcomes than our simulations, which only create one possible universe, have led us to believe. The implications of this galaxy that shouldn't be there ripple outward, touching on the fundamental practice of cosmology. It serves as a crucial reminder that a model, no matter how successful, is not reality. It is a simplified representation that must constantly be tested against observation. This lone galaxy is a stress test for the lambda CDM model, and while the model is robust enough that it is not yet broken, it is certainly being bent. Finding more of these isolated galaxies will be key. If they remain extremely rare, they can be dismissed as cosmic accidents. But if new, more sensitive telescopes begin to find that the voids are speckled with many such faint galaxies, it would indicate a serious flaw in our understanding of how dark matter behaves or how galaxies emerge from the primordial gas. This solitary sentinel in the void is therefore more than an oddity. It is a guidepost pointing toward either a refinement of our known physics or a doorway into entirely new physics, reminding us that the universe's greatest lessons often come from its most unexpected placements. Beyond the serene spiral of a dying solar system, the universe sometimes speaks in a language of pure, unfiltered energy, sending out signals so powerful they can outshine an entire galaxy in a fraction of a second. This brings us to one of the most electrifying mysteries of modern astronomy, the fast radio burst. For years, these events were cosmic one-hit wonders, brief blips of radio energy that appeared randomly across the sky and vanished without a trace, leaving astronomers baffled. But then, a discovery changed everything. A burst designated FRB 180916 was found to be not just a repeater, but a repeater with a clockwork rhythm, flashing on a predictable 16-day cycle. This transformation from a random flash to a punctual beacon has turned a deep mystery into an even deeper one, offering our first real clue to understanding what these colossal cosmic explosions could be. Imagine a flash of radio waves that carries more energy than the sun releases in 80 years, all compressed into a few thousandths of a second. That is the raw power of a fast radio burst. When the first ones were detected, the leading theories were equally cataclysmic. The final, dying screams of stars being devoured by black holes, or the collision of ultra-dense neutron stars. These are events so violent they can only happen once, which perfectly explained why the bursts seemed to be solitary events. The discovery of a repeating FRB shattered that simple picture. It meant the source couldn't be destroyed. It had to survive its own outburst and be capable of producing them again and again. But the 16-day cycle of FRB 180916 added a layer of complexity that was both a gift and a profound challenge. The pattern is unmistakable. It erupts for about 4 days, with multiple bursts happening at irregular intervals within that window, and then falls completely silent for 12 days before the entire cycle starts again. This isn't just repetition, it's a cadence, a heartbeat on a cosmic scale, and it points directly to a physical mechanism that is modulating the burst. The most compelling natural explanation involves the intricate dance of orbital motion. Picture a binary system where two objects are locked in a gravitational embrace. One of them is the engine of the bursts, most likely a highly magnetized neutron star known as a magnetar. These objects possess magnetic fields so intense they could strip the information from a credit card from a distance halfway to the moon. The thinking is that as this magnetar travels along its 16-day orbit around a companion star, its environment changes dramatically. For the 4 days when it's actively bursting, it might be passing through a region of space where its powerful magnetic field interacts with a dense wind or a disk of material flowing from its companion. This interaction could funnel material onto the magnetar's surface, triggering colossal starquakes or magnetic reconnection events that release the titanic bursts of radio energy. Then, for the following 12 days, the magnetar moves into a clearer part of its orbit, where the source of fuel is cut off, and the bursts cease until the cycle begins anew. This model elegantly uses the clockwork of orbital mechanics to explain the on and off pattern we observe. A second, equally fascinating possibility doesn't require a companion at all, but instead focuses on the slow, graceful wobble of the neutron star itself. This phenomenon, known as precession, is like the wobble of a spinning top as it slows down. If a magnetar is precessing, its rotational axis slowly traces a circle in space over a period of days or weeks. The incredibly powerful beams of radiation that these objects emit are thought to be shot out from their magnetic poles, much like a lighthouse. If the star is wobbling, those beams will sweep across the cosmos in a predictable pattern. From our vantage point on Earth, the radio beam might only point in our direction for a few days out of its full precession cycle, creating the active window we detect. The rest of the time, the lighthouse beam is pointing away from us, resulting in the observed silence. In this scenario, the 16-day cycle is not an orbital period, but the precession period of a solitary, wobbling stellar corpse. What makes this regular pattern so challenging for astronomers is that it narrows down the possibilities while simultaneously making the true source more enigmatic. An orbital period of 16 days suggests the companion object cannot be another super-dense neutron star or black hole, as such a tight orbit would be wildly unstable. Instead, the companion is likely a massive, young star which presents its own problems. The environment around such a star is chaotic, filled with violent winds and intense radiation that should scatter and smother the faint radio signals, making them incredibly difficult to detect across millions of light years. The precession model, while elegant, requires the neutron star to be wobbling at a very specific rate that is difficult to achieve and maintain. The very predictability of the burst, the fact that we can set our watches by its cycle, is what makes it so hard to explain with known physics. It's a clue that feels like it should solve the mystery, but instead it has deepened it, forcing us to consider that the true engine behind these bursts may be an even more exotic object or process than we have yet imagined. This regular FRB is a cosmic metronome ticking away in the darkness, and with each tick, it challenges us to rethink our understanding of the most extreme physics in the universe. While the rhythmic flash of a fast radio burst speaks to the energetic violence of stellar corpses, our next discovery reveals a world of such extreme and bizarre beauty that it seems more like a product of fantasy than physics. Imagine a planet where the forecast is not for rain but for liquid gemstones. This is the reality on WASP 121b, an exoplanet so intensely heated by its parent star that its atmosphere has become a crucible for creating clouds of titanium and other precious metals. This ultra-hot Jupiter, a class of gas giants that orbit perilously close to their stars, pushes the concept of extreme weather into a realm we never thought possible, offering a glimpse into the stunning diversity of planetary environments across the galaxy. The conditions on this world are almost incomprehensible. WASP 121b orbits its star in a blistering 30-hour cycle, so close that its day side is permanently locked facing the stellar inferno. Temperatures there soar to a staggering 2,500 degrees Celsius, hot enough to melt iron and vaporize rock. At such extremes, the very chemistry of the atmosphere undergoes a radical transformation. On a more temperate world like Earth, clouds form when water vapor cools and condenses into liquid droplets. But on this scorching giant, the atmospheric heat is so immense that molecules of titanium oxide and other metallic compounds, which would normally remain stable as gases, are forced to condense directly into liquid droplets or solid particles, creating high-altitude clouds of vaporized metal. The process is akin to steam rising from a boiling kettle. Only here the steam is composed of elemental ingredients you would typically find in a star's core or a spacecraft's heat shield. Astronomers were able to make this astonishing discovery not by taking a direct picture of the planet, but by analyzing its light with a technique called spectroscopy. As WASP 121b passes in front of its star, a small fraction of the star's light filters through the planet's thin atmospheric rim. Different elements and molecules in the atmosphere absorb specific wavelengths of this light, leaving behind a unique barcode of dark lines in the spectrum. When scientists decoded this barcode, they found the unmistakable signature of titanium oxide. The presence of this compound in the gas phase was the first major clue, but the real breakthrough came from studying the planet's phases. By observing the subtle changes in light as the planet orbits, revealing its day side and night side, researchers detected a telling asymmetry. The planet's day side, facing the star, was significantly brighter than its night side. The most plausible explanation for this reflective glare is a permanent, high-altitude layer of clouds made of highly reflective materials, with titanium-based compounds being a prime candidate. These metallic clouds act like a giant global mirror, efficiently bouncing a tremendous amount of the star's light back into space before it can be absorbed and converted into even more heat. The existence of such a world forces a dramatic rethink of atmospheric dynamics on gas giants. It reveals that the conditions for cloud formation are not limited to the familiar substances of water and ammonia. Under enough heat and pressure, the periodic table itself can become a source of weather. This discovery also provides a crucial link in understanding the wide spectrum of hot Jupiter atmospheres. Some of these worlds appear surprisingly dark, absorbing almost all the light that hits them, while others, like WASP 121b, are exceptionally bright. The difference may come down to the presence or absence of these reflective metal clouds, which in turn depends on the precise temperature and chemical composition of the atmosphere. A planet that is just a few hundred degrees cooler might not be hot enough to vaporize these metals, leading to a completely different atmospheric structure and appearance. This makes WASP 121b a key benchmark, a natural laboratory for studying how chemistry and climate interact under the most punishing conditions imaginable. It stands as a dazzling testament to the fact that the universe's creativity knows no bounds, crafting worlds where the sky itself shimmers with the essence of stars. But if the rhythmic ticking of a repeating fast radio burst represents a newly discovered type of cosmic clock, our next discovery reveals the face of a timepiece on a scale so vast it defies comprehension. We now journey to the heart of a distant galaxy cluster, where astronomers have observed a supermassive black hole not merely consuming its surroundings, but actively blowing a gargantuan, spherical bubble of searing plasma into the depths of intergalactic space. This is not a delicate structure, it is a titanic cavity, a cosmic void carved by the most powerful sustained eruption in the universe since the Big Bang itself. The discovery of this black hole bubble provides a stunningly clear snapshot of a process that, until now, had been largely theoretical. The profound and dramatic feedback that these gravitational monsters exert on their entire cosmic neighborhood. The story of this bubble begins with the incredible energy budget of a feeding black hole. When a supermassive black hole at the center of a galaxy actively pulls in vast quantities of gas, that material doesn't fall in silently. It forms a superheated, swirling accretion disk, and not all of that matter is destined to cross the event horizon. Through processes that are still not fully understood, but likely involving the black hole's powerful magnetic fields, a significant portion of the inflowing material is channeled and blasted outward in two opposing relativistic jets. These jets are like cosmic blowtorches composed of charged particles traveling at nearly the speed of light. As they plow through the galaxy's own gas and beyond, into the even more tenuous gas that fills the space between galaxies in a cluster, they do not simply bore a neat hole. Instead, they inflate a massive, buoyant bubble of ultra-hot plasma at their leading edges, much like a blow-dryer creating a bubble in a glass of water. The energy required to create such a structure is almost beyond imagination. The bubble's total energy content can be equivalent to the simultaneous explosion of billions of supernovae, released not in a single instant, but over millions of years in a continuous, focused outflow. The impact of this bubble on its surroundings is nothing short of transformative. It acts as a fundamental regulator of galaxy growth, a process astronomers call AGN feedback, with AGN standing for active galactic nucleus. Galaxy clusters are filled with a hot, diffuse gas known as the intracluster medium. This gas is the primary reservoir of fuel for future star formation within the cluster's hundreds of galaxies. Left to its own devices, this gas should gradually cool, condense, and fall into the galaxies, triggering immense waves of new star birth. But the black hole bubble disrupts this entire cycle. As the bubble expands, it creates a powerful shockwave that heats the surrounding intracluster medium, preventing it from cooling and collapsing. It's a cosmic thermostat. When the black hole feeds too greedily, it triggers an outburst that heats the gas so effectively that it shuts off its own future fuel supply. This feedback loop is crucial for explaining why we don't see galaxies growing to unimaginably large sizes. The central black hole essentially puts a ceiling on growth, preventing the galaxy from becoming too massive. Observing this process directly has been a landmark achievement. The bubble itself is invisible in optical light, but it reveals its presence in two ways. First, it can be seen in exquisite detail by X-ray telescopes like the Chandra X-ray Observatory. The hot plasma within the bubble glows brightly in X-rays, while the even hotter shockwave at its edge creates a distinct, sharp boundary in the X-ray emission from the intracluster gas. Second, when the jets from the black hole interact with magnetic fields permeating the cluster, they cause electrons to spiral at near light speed, emitting radio waves. This often creates two brilliant radio lobes on either side of the bubble, marking the points of impact. By combining X-ray and radio observations, astronomers can create a complete picture of this cosmic excavation project, measuring the bubble's size, its expansion speed, and the tremendous energy required to inflate it. This allows them to calculate the black hole's power output over its active lifetime, providing a direct measure of its influence on the evolution of the entire galaxy cluster. The bubble is therefore more than just an eruption. It is a fossilized record of the black hole's past activity, a permanent scar on the face of the cluster that tells the story of how a single, dark heart can govern the fate of thousands of galaxies. Leaving behind the titanic violence of black hole bubbles, we now witness a cosmic interaction of surprising delicacy and coordination. Our journey brings us to a pair of dwarf galaxies engaged in a gravitational ballet so precise that it hints at an unseen choreographer. These two small galaxies, known collectively as NGC 3227, are locked in a mutual orbit, circling each other in the vast halo of a larger spiral galaxy. Such galactic dances are not uncommon. What makes this pair an extraordinary oddity is the mysterious synchronization of their stellar populations. Despite being separate entities, the stars within both galaxies are almost identical in age and chemical composition. It's as if two distinct forests growing on different mountains were found to contain trees of the exact same species, height, and age. This cosmic coincidence challenges the standard picture of galaxies evolving in isolation, suggesting instead that their fates can be deeply intertwined from birth. The synchronization presents a fascinating puzzle because dwarf galaxies of this type are typically thought to be ancient relics, forming the bulk of their stars in a single, intense burst more than 10 billion years ago. After this initial period, they are believed to have largely run out of gas, becoming stagnant and fading slowly over eons. If these two galaxies had evolved independently, the random processes of star formation and supernova enrichment should have left each with a unique stellar fingerprint. The fact that they match so closely implies a shared history that is far more intimate than a simple orbital partnership. One compelling explanation is that they were born together from the same primordial cloud of gas and dark matter in the early universe. In this scenario, the two galaxies would have formed as a single, coherent structure that later fragmented into the pair we see today. Because they originated from the same raw materials at the same time, their stars would naturally share a common age and initial chemical makeup, like siblings born from the same parents. However, the story doesn't end with a shared birth. To maintain such synchronization over billions of years, something must have prevented each galaxy from forging its own independent path. This is where the invisible hand of dark matter becomes a central character in the narrative. Every galaxy is thought to be embedded within a vast, diffuse halo of this mysterious substance. The leading theory suggests that this pair of dwarfs is not only orbiting each other, but is also embedded within a shared dark matter halo. This common envelope of invisible mass would act as a stabilizing cocoon, regulating the flow of gas between the two galaxies and suppressing any independent star-forming activity. If one galaxy tried to capture a fresh cloud of gas to trigger a new wave of star formation, the gravitational influence of the shared halo might funnel that gas toward both galaxies equally, or perhaps even prevent the accretion altogether. This would keep both galaxies in a state of arrested development, forever mirroring each other's quiet evolution. The implications of this synchronized dance extend far beyond this one peculiar pair. It offers a rare glimpse into the role of dark matter on the smallest galactic scales. The stability and longevity of this system provide strong indirect evidence for the existence of these dark matter halos and their profound influence on galactic evolution. If dark matter were not present, or if it behaved differently, the gravitational bond between these two galaxies would likely be too weak to maintain their coordinated state over cosmic time. Their mutual orbit would have destabilized, or tidal forces would have torn them apart. The fact that they remain intact and synchronized suggests that their dark matter halos are providing the necessary gravitational glue to make this long-term partnership possible. This makes the system a natural laboratory for studying the properties of dark matter itself, particularly how it clumps and interacts on the scale of small galaxies. Furthermore, this discovery challenges the traditional hierarchy of galaxy formation. We often think of large galaxies growing by consuming smaller ones, a violent process of cosmic cannibalism. But here we see a cooperative alternative. Instead of one dwarf galaxy absorbing the other, they have maintained a stable, binary relationship for billions of years. This suggests that such long-lived galactic pairs might be more common than previously thought, especially in the quiet outskirts of larger galaxies. They represent a pathway of galactic evolution that is based on partnership rather than predation. Finding and studying more of these synchronized systems will help astronomers understand the conditions that allow for such delicate balances to arise and persist. It reveals a universe where gravity can create not only destructive collisions but also enduring, harmonious dances, a subtle counterpoint to the more dramatic clashes that typically dominate the cosmic story. And so we arrive at the final stop on our tour of cosmic oddities, a discovery that pushes our search for alien worlds to its absolute limit. After journeying past rogue planets with self-lit auroras and stars that breathe with a slow, steady rhythm, we now turn our gaze to a signal so faint and enigmatic that it straddles the line between a groundbreaking discovery and a tantalizing mirage. This is the story of the Phantom Examoon, the first potential moon ever detected outside our solar system, a world that, if confirmed, would open an entirely new frontier in the hunt for habitable environments. The candidate, known as Kepler 1625b, was found orbiting a gas giant planet some 8,000 light-years away, a system initially identified by NASA, a planet-hunting Kepler spacecraft. The method of detection was a masterclass in astronomical subtlety. Kepler's primary technique, the transit method, involves watching for the minuscule dip in a star's brightness that occurs when a planet passes in front of it. But in the case of the star Kepler 1625, the data held an extra layer of intrigue. The transits of the giant planet Kepler 1625b were not perfectly clean. Before the main dip in starlight began, and again just after it ended, astronomers led by David Kipping and his team at Columbia University detected additional, much smaller dips in brightness. It was as if a tiny shadow was preceding and trailing the planet's own, like a moon following its parent world in a graceful celestial procession. The team proposed that this pattern was the signature of a Neptune-sized examoon, a gargantuan companion so large it would dwarf every moon in our own solar system. Confirming such a faint signal, however, is a monumental challenge that highlights the very edge of our current observational capabilities. The main obstacle is that the evidence is inherently indirect and incredibly delicate. The tiny dips attributed to the moon are barely distinguishable from random noise in the starlight or from other potential sources of interference, such as starspots, the stellar equivalent of sunspots. Furthermore, the gravitational tug of a moon on its host planet would cause the planet's transit to wobble slightly in its timing, a second signature that could corroborate the finding. While the Kepler 1625b system showed hints of such timing variations, the data was not conclusive enough to rule out all other explanations. Subsequent observations with the Hubble Space Telescope were gathered in an attempt to settle the debate, but even Hubble's powerful eye could not deliver a definitive verdict. The signal remained stubbornly on the threshold of detection, a persistent ghost in the data that neither fully vanished nor came into sharp focus. This ambiguity has left the astronomical community divided, with the candidate simultaneously representing the most promising exomoon discovery to date, and a cautionary tale about the difficulties of finding such small objects across interstellar distances. Yet the profound implications of this potential discovery are what truly capture the imagination, extending far beyond the simple confirmation of another world. If a Neptune-sized exomoon is real, it would force a complete re-evaluation of how moons form. In our solar system, large moons like Ganymede or Titan formed from a disk of gas and dust that surrounded their infant parent planets. But a moon as massive as Neptune could not have formed this way around a Jupiter-sized planet. The disk would not have contained enough material. This suggests a far more dramatic origin story. Perhaps this candidate is not a moon at all in the traditional sense, but a captured planet. In the chaotic early days of the planetary system, the giant planet may have gravitationally snatched a smaller, free-floating world and forced it into orbit, a fate that some theories suggest could have almost happened to Mercury in our own solar system. The existence of such a captured world would indicate that planetary systems can be even more dynamic and violent than we currently believe, with entire worlds being stolen and repurposed as moons. Most compellingly, the search for exomoons is inextricably linked to the search for life. While gas giant planets like Jupiter are themselves inhospitable, their large moons could be havens. We see this potential in our own backyard with moons like Europa and Enceladus, which hide vast subsurface oceans beneath their icy shells. A Neptune-sized exomoon, especially one orbiting within its star's habitable zone, the region where temperatures could allow for liquid water, would be a prime candidate in the search for biosignatures. Such a world could potentially have a thick atmosphere and a rocky or liquid surface, offering a stable environment for chemistry to potentially blossom into biology. The phantom signal of Kepler 1625b, therefore, is more than just an astronomical curiosity. It is a beacon pointing toward a future where we might one day scan the atmospheres of moons, not just planets, for signs of life. It represents the thrilling next chapter in exploration, a reminder that the greatest discoveries often begin as the faintest of whispers, challenging us to build better telescopes and ask even bigger questions of the cosmos. And so our journey through the cosmos reaches its end for now. We have ventured from the profound chill of the great cold spot to the sparkling diamond planets, from the ghostly silence of dark galaxies to the rhythmic heartbeat of a breathing pulsar. We have witnessed worlds with metal clouds, stars that flicker with no clear cause, and black holes that paint bubbles on a galactic canvas. Each of these 30 discoveries is a testament to a simple, humbling truth. The universe is under no obligation to conform to our expectations. It is a place of infinite creativity where the rules are written in a language we are only just beginning to decipher. These anomalies are not simply errors in our map of reality. They are the signposts pointing toward the blank spaces, the places where our current understanding ends and a new, more profound truth begins. The true value of these cosmic oddities lies not in their ability to baffle us, but in their power to inspire. Every bizarre signal, every impossible galaxy, every runaway star is a direct challenge to the scientific community. They are the puzzles that will occupy the brightest minds for generations, driving the development of new telescopes, new theories, and new ways of seeing. The discovery of a galaxy that shouldn't exist forces us to question our most fundamental models. The detection of an interstellar visitor like Oumuamua opens an entirely new field of astronomy. Each one is a catalyst, ensuring that our quest for knowledge never becomes stagnant or complacent. They remind us that science is not a collection of settled facts, but a living, breathing process of inquiry. a continuous conversation with the cosmos where the most exciting answers are always the ones that lead to even more profound questions. As we look back on this incredible tour, from the vast architecture of the cosmic web to the intricate death spiral of a white dwarf, it's clear that we are living in a golden age of discovery. Instruments like the James Webb Space Telescope and the Vera C. Rubin Observatory are not just showing us more of the universe, they are revealing a universe that is stranger, more dynamic, and more wonderfully bizarre than we ever dreamed. The map is being redrawn in real time, and we all have a front row seat. So we leave you with this thought: which of these 30 oddities reshaped your view of reality the most? Was it the star older than the universe, or the galaxy missing its dark matter? The Phantom Exomoon or the Candy Cane Nebula? Share your favorite cosmic mystery in the comments below. We are genuinely curious to hear which discovery captured your imagination. If you enjoyed this voyage to the edge of understanding, please show your support by liking this video and subscribing to the channel for more journeys into the unknown. The universe has countless more secrets waiting to be uncovered, and we can't wait to continue exploring them with you.